Hello. Guys, can you hear me now? Can you hear me now? It should be okay now. Yeah, is it all okay? Perfect, perfect, perfect. So quickly give me some green signal now from the chats if all of you can hear me. If I'm perfectly audible and visible to everyone. Quickly, quickly, quickly. Quickly, guys. Everyone, everyone. I think yes, you all can hear me now. I'm perfectly audible and visible to everyone. All right, that's great. Perfect, people. Perfect, perfect, perfect. I thought the session is gone, huh? All right, guys. So, as you all must be knowing, today we are starting one more chapter. And this chapter belongs to your inorganic chemistry, basically. One of the most important chapters of your inorganic chemistry, which forms the basis of organic chemistry as well. Okay? And the name of the chapter, you all must be knowing, it is chemical bonding. Right? So, my dear students, before starting this particular session, before starting the chemical bonding chapter, let me tell you, from this particular chapter alone, almost 3 to 4 questions are asked every year in your NEET as well as JEE examination, right? And we shall be starting this particular chapter from the basics, from the scratch itself. So are you guys ready for it? Are you guys ready for it? Yes? Say yes or no in the chats, quickly. Are you ready for it? So the ones who have not liked the session yet, I would want every one of you to like the session, to share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for everybody. And at the same time, if you're not subscribed to this particular Your Unacademy NEET English yet, I would want you guys to do that as well. Okay? So do like this session, share this particular video with everyone, and at the same time, do subscribe to the channel as well, my dear students. Okay? Yes, exactly. Even JEE students can also watch it. No issues at all. Yeah? Should we start then? I need a lot of fire symbols in the chats. I need a lot of fire symbols in the chats. Then only I'm going to start the session. Quickly. Quickly, my dear students. I need a lot of fire symbols in the chats. Yeah? Perfect, people. Perfect, perfect, perfect. And let me tell you one more thing. Whatever I'll be writing on the screen, I would want you guys to take a note of every single thing. Because every single thing in this chapter is equally important. Every single point is important. And again, I'm telling you, I'll be starting from the exact basics. Okay? Perfect, guys. So, let's get to know, first of all, what chemical bond exactly is all about. How do you define a chemical bond? I'm sure this is something which every one of you must be knowing, right? What is a chemical bond? My dear students, any force of attraction that holds the atoms together in a molecule. Any force of attraction that holds the atoms together in a molecule, that is something which you call as chemical bond, right? Now, dear students, these chemical bonds, these are of different types basically, okay? And we have to discuss all these different chemical bonds one by one. So first of all, let me tell you, any force of attraction that holds the atoms together in a molecule, that force of attraction is something which you call as chemical bond. Now, there are different types of chemical bonds which we have to study one by one. So, my dear students, I'm starting the chapter with a term called as ionic or electrovalent bond. This is the first type of bond which we shall be discussing in today's session. Ionic or electrovalent bond. First of all, how do we define the ionic bond? As you can see this particular definition, it is the chemical bond formed between the atoms due to complete transfer of electrons. Now the point is, what is meant by it? What is meant by it? Let's try to understand this in detail. My dear students, for example, if I talk about NaCl solid, let's say I'm talking about NaCl solid, sodium chloride. One thing which I'm sure all of you must be knowing, this sodium over here, it is a metal basically, and chlorine right here, what is it? It is a non-metal. It is a non-metal. This is something which everyone must be knowing. Sodium is the typical example of the metal, and chlorine, it is the typical example of the non-metal. Now, my dear students, you all must be familiar with the fact metals have got high tendency to lose electrons, right? Metals, they have got high tendency to lose electrons because metals are electropositive in nature. They are electropositive in nature. They have got high tendency to lose electrons. Whereas, if I talk about the non-metals have got strong tendency to gain electrons. They have got strong tendency to gain electrons, right? Now, dear students, try to understand one thing. Let's see exactly how this NaCl would have got formed. How this NaCl would have got formed. If you talk about sodium, sodium belongs to group first. It's a group first element, you all must be knowing. And all the group first elements, they have got one electron in their outermost shell. So, if I particularly talk about sodium, it has got one electron in its outermost shell. Now, my dear students, if it has got one electron in its outermost shell, is it easy for sodium to lose one electron or to gain 7 electrons? I must say it is easy for sodium to lose one electron. So, if I talk about sodium, it is going to lose one electron and it's going to get converted into Na positive, right? This particular sodium over here, it is going to lose one electron and it is going to get converted into Na positive. Now, my dear students, the electron which is lost by sodium completely, this particular electron will be gained by chlorine. Chlorine is going to gain one electron and it will get converted into Cl negative over here, right? So, my dear students, can I say, since sodium has lost one electron, so it got converted into Na positive. Similarly, chlorine has gained one electron, so it got converted into Cl negative. So what do you see over here? My dear students, as you can see, cation and anion formation took place. Sodium lost an electron, got converted into cation. Chlorine gained an electron, got converted into an anion. So can I say I have got equal and oppositely charged species over here? Yes, I have got equal and oppositely charged species over here. And whenever you have got equal and oppositely charged species, what kind of force of attraction will be between them? My dear students, this particular force of attraction is something which you call as electrostatic force of attraction. This is the electrostatic force of attraction between the cation and anion. So, let me tell you the electrostatic force of attraction between the cation and the anion. This electrostatic force of attraction is something which you call as ionic bond. Or my dear students, you can call it as the electrovalent bond as well. You can call it as the electrovalent bond as well. Okay. So first of all, this particular sodium, it has lost one electron completely. And this chlorine, it has gained one electron completely. The electron which was given by sodium, chlorine has gained that one electron completely. So can I say complete loss and gain of electrons is taking place over here? And my dear students, the bond which gets formed due to complete loss and gain of electrons, that bond is something which basically you call as electrovalent bond, or you can call it as the ionic bond as well, right? So let me know quickly in the chats if this particular simple definition of ionic bond is clear. Give me some thumbs up in the chats quickly. Quickly, my dear students. Quickly, my dear students, in the chat. So I took the example of sodium chloride. Sodium is the example of metal. Chlorine is the non-metal. Sodium has got the high tendency to lose electron. Chlorine has got high tendency to gain electron. So sodium will be losing one electron and chlorine will be gaining the same electron, due to which we got an cation and we got the anion. So there will be electrostatic force of attraction between them. And this electrostatic force of attraction is something which you call as ionic bond, or you can call it as electrovalent bond as well. Okay? And do remember from now onwards, the bond which gets formed due to complete loss and gain of electrons, that bond is something which you call as electrovalent bond or ionic bond, right? The choice is all yours. Okay? Perfect. So I'm sure the term ionic bond is absolutely clear to you, right? Now, my dear students, if I ask you, what are the favorable conditions? If I ask you, what are the favorable conditions for the formation of ionic bond? For the formation of ionic bond. The favorable conditions for the formation of ionic bond. What do you exactly think about it? My dear students, I must say, since I told you exactly how ionic bond formation takes place. First of all, metal loses the electron, then non-metal gains the electron, then cation gets formed, anion gets formed, and there will be force of attraction. And that force of attraction is what you call as ionic bond. So what should be the favorable conditions for the formation of ionic bond? The first condition, I must say, I would say, one element should be metallic. One element should be metallic in nature, and another element should be non-metallic in nature. Another element should be non-metallic in nature. I'm sure everyone got it properly. One element should be metallic in nature, and another element, it should be non-metallic in nature. Why is that? Because if one element will be metallic, then only it's going to lose electrons. Then only cation will form easily. Similarly, one element should be non-metallic in nature so that it can gain electron, so that anion gets formed easily. And the ease with which cation and anion forms, the ease with which cation and anion formation takes place, I would say, those will be absolutely the favorable conditions for the ionic bond to get formed, right? Basically, cation should get formed easily, anion should get formed easily, right? And how cation will get formed? If one element will be metallic, and how anion will get formed? If one element will be non-metallic in nature, right? Now, my dear students, since metal has to lose electrons, that metal which is going to lose electron easily will form the cation easily, right? So can I say the metal should have, low ionization energy? Metal should have low ionization energy. Then only cation formation will take place easily, right? Similarly, if I talk about the non-metal, can I say non-metal should have high electron affinity? Right? Non-metal should have high electron affinity. Then only the non-metal is going to attract the electron easily towards itself, so that anion formation will take place easily, right? So basically, for the formation of ionic bond, cation should get formed easily and anion should get formed easily. And cation will only get formed easily if the metal has a low ionization energy. Anion can only get formed easily if the non-metal has got high electron affinity. Perfect. So these are the favorable conditions for the ionic bond to get formed. Okay? Is this clear to everyone? Is this clear to everyone, people? Quickly in the chats. Is this point clear to everyone? So, what are the favorable conditions for the ionic bond to get formed? First point, one element should be metallic in nature, another element should be non-metallic in nature, right? Metal should have low ionization energy, then only it can be a good candidate for the formation of ionic bond. Similarly, non-metal should have high electron affinity, then only it can be a good candidate for the formation of ionic bond. Perfect. Right? What happens exactly? That metal which has got low ionization energy, it forms cation easily, right? It forms cation easily. And similarly, that non-metal which has got high electron affinity, it forms anion easily, right? Perfect. And the ease with which cation and anion formation takes place, that decides basically your covalent bond, that defines your ionic bond strength, etc. and all, which we are going to discuss one by one. I hope it's clear to everyone. Okay. Now, dear students, if you talk about these ionic compounds, well, there are some characteristics of the ionic compounds which you all must be knowing. Okay. The first point over here, the ionic compounds, they are generally hard. Why is that? Because in case of ionic bonds, there is strong electrostatic force of attraction. And due to strong electrostatic force of attraction, these ionic compounds, they are generally hard, right? Since strong electrostatic force of attraction is between the cation and anion, that is the reason why your ionic compounds have got high melting and boiling point as well. That is the reason why they have got high melting and boiling point as well. Okay? At the same time, due to the strong electrostatic force of attraction between the cation and anion in the ionic compound, we say these ionic compounds, they have got high density as well, right? Now, my dear students, look at this particular point and try to understand it. Try to understand. My dear students, when you talk about the ionic compounds, they are insulators in solid state. But in molten and aqueous state, they behave like good conductors of electricity. What that means? For example, if I've got sodium chloride in solid state, let's say I've got sodium chloride in solid state. So over here, sodium is basically Na positive, and this is Cl negative, and there is strong electrostatic force of attraction. My dear students, due to the strong electrostatic force of attraction, these ions cannot move over here, right? If the ions cannot move at all, I would say in solid state, your ionic compounds, they are going to behave like insulators, right? Because of the strong electrostatic force of attraction in the solid state. Now, for example, imagine that I'm going to convert this NaCl solid into NaCl liquid. That means I'm going to convert this NaCl solid into NaCl liquid. This NaCl liquid is something which I call as molten NaCl. First of all, think about it. How I would have converted this solid into liquid. I would have converted the solid into liquid by supplying heat, right? And my dear students, you already know, when this solid would have got converted into liquid, what would have happened to the distance between the ions? Can I say distance between the ions would have increased? And if the distance between the oppositely charged ions increases, force of attraction decreases. And if the force of attraction decreases, can I say now the ions over here can comparatively move, right? Due to that, I must say the molten NaCl, it does not behave like the insulator. It behaves like the conductor. I hope this particular point is clear to everyone. Similarly, my dear students, if you talk about NaCl aqueous, what is meant by NaCl aqueous? That means you have taken NaCl and you have introduced NaCl into water. What would have happened? NaCl would have got broken down first into Na positive and Cl negative. And those Na positive and Cl negatives would have got hydrated, right? Water molecules would have been attached to Na positive and Cl negatives. Perfect, right? So I must say, the hydrated Na positives and Cl negatives, they can easily move, right? And if they can move, that means they are also going to behave like the conductors. So one simple thing which you are going to remember from here, whenever you talk about ionic compound, an ionic compound, when present in solid state, it behaves like the insulator. When the ionic compound is present in liquid state, it behaves like the conductor. When the same ionic compound is present in its aqueous state, it again behaves like the conductor as well, right? This particular point, I'm going to let you know in some time in detail when I'll talk about hydration energy. Okay? So quickly let me know in the chats if all the things are clear till here. If you talk about ionic compounds, in case of ionic compounds, there is strong electrostatic force of attraction between the ions, due to which these ionic compounds are generally hard. They have got high melting and boiling point. They are conductors, they are insulators in solid state, but in molten state or aqueous state, they behave like the conductors. And since due to the strong electrostatic force of attraction, they have got high density as well. Clear till here? Quickly, let me know in the chats if all the things are clear. If all the things are clear, let's try to understand few important terminologies which are related to these ionic compounds. Terminology number one. Terminology number one. That is lattice energy. That is lattice energy. So, my dear students, how do you define the term lattice energy? There are two ways by means of which you can define the term lattice energy. The first definition I've mentioned over here. And what is this definition all about? The amount of energy which is released when 1 mole of an ionic lattice is formed from its constituent gaseous ions. What is meant by that? Before talking about this particular definition, I would want you guys to remember one thing, one simple thing. My dear students, for example, I have got a cation in this hand, I have got an anion in this hand, right? Cation and anion. What will happen? There will be electrostatic force of attraction between them. Do remember, due to attractions, whenever there are attractions between the atoms, between the ions, between the molecules, due to attractions, do remember, always energy is released, right? So attractions between any two species, it always leads to a release in the energy. This is something which I would want you guys to remember right now, okay? So whenever there will be attractions between any two species, be it ions, be it atoms, be it molecules, due to attractions, do remember, energy is released. Energy is released. This is the first point which you should know. Now, my dear students, understand one thing. Any process in which energy is released, what do we call that process? We call that particular process exothermic process. We call that particular process exothermic process. You all must be knowing that. And for all the exothermic processes, delta H value is taken to be negative. This is something which you should know. Okay? Now, people, over here, if you look at this particular example, in this particular example, can I say 1 mole of ionic compound is being formed? Through this particular reaction, you can see 1 mole of ionic compound is being formed when the constituent elements of this ionic compound, when they are present in their gaseous ionic forms. In this particular example, I can say 1 mole of ionic compound is formed from its constituent gaseous ions, right? As you can see, this is positive, this is negative. So there would have been attractions. Due to attractions, energy would have been released, right? So my dear students, that amount of energy released when 1 mole of ionic solid is formed from its constituent gaseous ions, that amount of energy released is something which you call as lattice energy, right? Perfect. So do remember this particular point. The amount of energy which is released when 1 mole of ionic solid is formed from its constituent gaseous ions, that amount of energy released is something which you call as lattice energy. So since in this particular process, as you can see, in this particular process, energy is released, so I can say delta H lattice for this process over here, it is going to be negative. Okay, delta H for this particular process is going to be negative. Well, I can define lattice energy in one more way as well. I can say lattice energy, it is the amount of energy required to break 1 mole of ionic lattice. To break 1 mole of ionic lattice into its constituent gaseous ions. Now, what is meant by that? What is meant by this particular definition? My dear students, imagine that you have got 1 mole of NaCl. Imagine that you have got 1 mole of NaCl solid, right? You have got an ionic compound. You have got 1 mole of ionic compound. Over here, this is Na positive, this is Cl negative. So there is electrostatic force of attraction between these ions, right? Now, dear students, you Tell me one thing. If I want to break this force of attraction, between the ions, what do I need to do? In order to break the force of attraction, I will have to supply energy. For example, I'm supplying energy, right? I'm supplying energy and I'm breaking this force of attraction in such a way that this ionic solid, it is getting converted into its constituent gaseous ions. It is getting converted into its constituent gaseous ions. So what did I do? I took 1 mole of NaCl, 1 mole of ionic compound. Over here, you have got Na positive, Cl negative. There are attractions between them. If you want to break these attractions, you have to supply energy. Energy is required to break these attractions. My dear students, the amount of energy which is required to break 1 mole of ionic compound, into its constituent gaseous ions, that is also what you call as lattice energy. And in this particular process, energy is required. And any such process in which energy is required, that's what you call as endothermic process. So over here, this particular process, if I can say, this particular process over here, it is endothermic in nature. And in all the endothermic processes, delta H is going to be positive in nature. So I would say in this process, delta H lattice is going to be positive. It is going to be positive. Perfect. Over here, delta H lattice was negative. Right here, delta H lattice is taken to be positive. Magnitude-wise, both the things will be same. Perfect. It is just this negative sign tells you that energy is released and this positive sign tells you that energy is absorbed. Imagine that. In the first example, delta H value is minus X kilojoules. So since I've just reversed the things, so over here, I would say delta H lattice will be plus X kilojoules. Magnitude-wise, both will be same. It is just the sign will be reversed. That's it. Okay? Perfect. So I hope you got the idea of what this lattice energy exactly is all about. My dear students, if you look over here, if you look at the second part, we are breaking the force of attraction. Which kind of force of attraction we are breaking? We are breaking the electrostatic force of attraction. And you all must be knowing, electrostatic force of attraction is directly proportional to the product of charges and inversely proportional to the distance, right? Electrostatic force of attraction, it is directly proportional to the charges and inversely proportional to distance cut square, right? Can I say that ionic compound which has got more charge on its ions, will have more electrostatic force of attraction, and in order to break that force of attraction, you have to supply more energy, right? So can I say one simple statement, that ionic compound in which the ions have got more charge will have more lattice energy, right? Yeah? Perfect. Similarly, the electrostatic force of attraction is inversely proportional to distance cut square as well, right? Or in short, I can directly say force of attraction between the ions, it is inversely proportional to distance. Can I say those ions which are lesser in size, can I say they'll be comparatively close? And if those ions will be comparatively close, the distance between the ions will be less. And if the distance between the ions is less, force of attraction between the ions will be more. And if the force of attraction is more energy is needed to break the bond, right? So I can say lattice energy will be more. So on how many factors this lattice energy will depend upon? This lattice energy will depend upon 2 factors. Charge present on the ions. Number 2, size of the ions. If this thing is clear to everyone, just let me know once quickly in the chats. Lattice energy, if I talk about the lattice energy is directly proportional to the charge present on the ions. And it's inversely proportional to the size of the ions. Is this clear to every single guy? Quickly, let me know in the chats. More the charge present on the ions, more is going to be the lattice energy. Lesser the size of the ions, lesser will be the distance between the ions. More will be the force of attraction between the ions. and more energy is needed to break that. That means indirectly you are saying more is lattice energy, right? I hope this particular point is clear to everyone. Quickly, tell me the answer of these two questions over here. The first question, LiCl, NaCl, KCl, RbCl. You have to arrange them on the basis of their increasing lattice energy. Arrange them on the basis of their increasing lattice energy. Now guys, understand. This is Li positive over here. This is Cl negative. Na positive, Cl negative. K positive, Cl negative. Rb positive, Cl negative. Can I say in all these examples, anion is same everywhere? Anion is same. So you're not going to decide on the basis of anion. Leave anion aside. You're not going to decide on the basis of anion. So you should be deciding on the basis of cation. You should be deciding on the basis of cation. Now, my dear students, the charge on every cation over here is same. So you're not going to decide on the basis of charge. You're not going to decide on the basis of charge. You'll be deciding on the basis of size. You know, lattice energy, that is inversely proportional to what? That is inversely proportional to size. Over here, you have got Li positive, Na positive, K positive, Rb positive. So Li positive, Na positive, K positive, Rb positive. If I ask you, on moving from top to the bottom, what happens to ionic size? On moving from top to the bottom, what happens to ionic size? On moving from top to the bottom, ionic size increases. And if ionic size increases, I must say lattice energy decreases. Lattice energy decreases. Perfect. So that particular ion which will be having lesser size, that's Li positive, which will be having lesser size, will have maximum lattice energy. So this is the order of the lattice energy, as simple as that. Right? Simple and basic. Look at the second one. Look at the second example. Over here, magnesium is present in di-positive state, oxygen in di-negative state. Sodium in +1 state, chlorine in -1 state. Lithium +1, chlorine -1. Right? First of all, if you look at the first compound, in the first compound, the charge on the ions is maximum. And first, you'll be giving priority to charge. First, you'll be giving priority to charge. So that particular compound in which the charge on ions is maximum will have maximum lattice energy. So first one is going to have maximum lattice energy. Now among these two, NaCl, LiCl. Anion in both the cases is same. So leave anion aside. Now talk in terms of cation. The charge on cation is same. So leave charge aside. Decide on the basis of size. Na positive, Li positive. Which one has got lesser size? Li positive has got lesser size. Lesser the size, more the lattice energy. So third will have more lattice energy, followed by 2. Let me quickly know in the chats if this is clear to everyone. Quickly, my dear students. Quickly, let me know in the chats if all the things are clear to everyone. Quickly. Yeah? Perfect, guys. Let's talk about a few more examples. Or before talking about a few more examples, let's deal with one more term, that is hydration energy. This is again one important term. First one was lattice energy, the amount of energy which is required to break 1 mole of ionic lattice into its constituent gaseous ions. Right? Perfect. Lattice energy, it depends on 2 factors, charge and size. Directly proportional to charge on ions, inversely proportional to size of ions. Now, what is hydration energy? Before talking about hydration energy, let's have a look exactly what hydration is all about. What hydration is all about. My dear students, imagine that you have got Na positive in gaseous state and you have got Cl negative in gaseous state as well. Okay? Imagine that. And at the same time, imagine that they are present in a container and this container, it contains water already. There is water inside the container. There is water inside the container and you have introduced Na positive and Cl negative. If I ask you about the structure of water, right? Over here, oxygen is more electronegative, right? So I would say oxygen will be having delta negative charge and hydrogen, they are less electronegative than hydrogen. So they'll be having delta positive charge. This is something which every one of you will be knowing. My dear students, this oxygen, I'll be calling it as negative end of water. And these hydrogens over here, I'll be calling them as positive end of water. Negative end of water, positive end of water. Now you have introduced Na positive into water. what is going to happen? Over here, it is a positively charged ion. Can I say the negative ends of water are going to approach this Na positive? Absolutely. The negative ends of water, they are going to approach this Na positive. So I would say the negative ends of water, they are going to approach this Na positive. Perfect. Because between the negative end of water and Na positive, there will be attraction. And whenever there is attraction, energy is released. This process in which water molecules are getting attached to the ions. Water molecules are getting attached to the ions. This process, this phenomenon is what you call as hydration over here. You'll be calling this phenomenon as hydration. In the similar way, you have got Cl negative over here. Towards the Cl negative, the positive ends of water are going to attach. The positive ends of water are going to attach towards Cl negative. Perfect. Between Cl negative and positive ends of water, there will be again attractions. And due to attractions, energy is released. And my dear students, this process in which the phenomenon in which water molecules are getting associated towards a particular ion, this is something which you call as hydration. So can I say Na positive right here is getting hydrated and even Cl negative right here is getting hydrated? Right? What is happening in the hydration process? What is happening? Between the ion and water, attractions are there. Whenever there are attractions, energy is released. Energy is released. Now remember, my dear students, the amount of energy released when 1 mole of gaseous ion undergoes hydration. Imagine that you have introduced 1 mole of Na positive in water. Imagine that you have introduced 1 mole of Na positive gas into water. Right? What will happen? Hydration of Na positive will take place, due to which energy will release. And the amount of energy released when 1 mole of gaseous ion undergoes hydration, that amount of energy released is what you call as hydration energy. Since energy is released in the process, therefore hydration, it's always exothermic in nature. So if I ask you, what about the delta H hydration sign? Delta H hydration sign, it's always going to be negative only, because the process is always exothermic. Perfect. So the amount of energy released when 1 mole of gaseous ion undergoes hydration, that's something which you call as hydration energy. Okay. Now, dear students, you must be thinking on what factors this hydration energy depends upon. Let me tell you, this hydration energy, it depends upon 2 factors. Hydration energy, it depends upon 2 factors. Number 1, charge present on the ion. Number 2, size of the ion. Number 2, size of the ion. Right? More the charge present on the ion, more water molecules are going to associated with the ion. And if more water molecules are being associated, more energy will be released. And if more energy is released, more is hydration energy. As simple as that. Right? I hope you're getting it. More the charge present on the ion, more is going to be the hydration energy. Okay? Number 2, lesser the size of ion. For example, you have got 1 ion of this much size, 1 ion of this much size. Okay? The charge present on both the ions is same. Can you tell me, among these 2 cases, where is the positive charge density more? I would say that ion which is lesser in size, its charge density will be more. More the positive charge density. Can I say more water molecules will get associated with it? And if more water molecules are getting associated with this particular thing, more will be the energy released. And if more is the energy released, more is the hydration energy. Okay? So do remember, that ion which is lesser in size will have more charge density. And due to more charge density, more water molecules will get associated. And if more water molecules are getting associated, that means more hydration energy in short. Right? Perfect. Perfect, guys. So more the charge on the ion, more water molecules getting associated, more hydration energy. Lesser the size of the ion, more charge density. More charge density means more water molecules getting associated. More water molecules getting associated means more hydration energy. In short, I hope this is clear to everyone. Okay. Now, dear students, let's try to solve these set of questions which can be asked. Have a look. We have to arrange these ions on the basis of their hydration energy. Hydration energy order. Now you tell me quickly. Li positive, Na positive, K positive, Rb positive. The charge on every ion is same. So you're not going to decide on the basis of charge. You'll be deciding on the basis of size. Right? Hydration energy and size, they are inversely proportional. Lesser the size of ion, more is going to be the hydration energy. Lesser the size of the ion, more is going to be the hydration energy. Done and dusted. Number two. What about the order of the size of these ions? Order of the size of these ions. Li positive, Na positive, K positive, Rb positive. You already know it. Li positive has got least size, followed by Na positive, followed by K positive, followed by Rb positive. Because you know, on moving from top to bottom, ionic size increases. Right? Now, my dear students, look at this particular case. This is what you call as hydrated size. Okay. I told you among all these ions, hydration energy of Li positive is maximum. Why is that? Because maximum water molecules are being attached towards Li positive. You know it. Because of its lesser size, maximum water molecules are attached. Right? For example, this is Li positive. This is Li positive. Let's say this is Na positive. Right? The size of Li positive is minimum. So maximum water molecules will be attached to it. Maximum water molecules will be attached to it. Right? Maximum water molecules will be attached to it. Comparatively towards Na positive. Comparatively towards Na positive. Less number of water molecules will be attached to Na positive. Now you tell me one thing. Li positive, the size of Li positive including the water molecules. The size of Li positive including the water molecules is what you call as hydrated size. This is something which I call as hydrated size of Li positive. This is something which I call as hydrated size of Na positive. So where do you see hydrated size more? Hydrated size is more in case of Li positive. Right? This is the hydrated size order. This is the hydrated size order. I hope this is clear. Right? At the same time, we have to discuss about the mobility. Mobility means the speed with which the ion moves. The speed with which the ion moves. Over here, I'm given with hydrated Li positive. This is hydrated Na positive, hydrated K positive, hydrated Rb positive. Which one? Which hydrated ion over here has got maximum size? It's Li positive aqueous, which has got maximum size. Maximum size means less mobility or more mobility. The one which will be having maximum size, that will be bulky in nature. If that is bulky in nature, the speed with which that ion moves, that will be less. Right? That will be less. So I must say, if I talk about the mobility of these hydrated ions, this is going to be the mobility order. Right? This is going to be the mobility order. And wherever the ion moves faster, wherever mobility is maximum, do remember conductivity is maximum there only. Do remember wherever mobility is maximum, the conductivity is maximum there only. Where is the mobility maximum? Rb positive aqueous. So conductivity will be maximum here only. So can you relate all these terms? Can you relate all these terms? Can you relate all these terms quickly? More the hydration energy, more is going to be the hydrated size. More the hydrated size, lesser is going to be the mobility. Lesser the mobility, lesser will be the conductivity. That's all. Yeah? Is it clear? Is it clear, guys? Quickly in the chats. Everyone. Quickly in the chats, if it is clear to everyone. Quickly in the chats. Quickly, guys. Yes or no? Is this part clear to everyone? So let me quickly summarize it, whatever I've said. Whatever I've said. Do remember one simple thing. Whenever we talk about hydration energy, I told you hydration energy, it's directly proportional to charge. It is inversely proportional to size, right? Number two, hydration energy. More the hydration energy, more is going to be the hydrated size. More is going to be the hydrated size. More the hydrated size, lesser will be the mobility of hydrated species. lesser is going to be the mobility of hydrated species, right? And how mobility and conductivity are related? Do remember, ionic mobility is directly proportional to conductivity. More the mobility means more the conductivity, lesser the mobility means lesser the conductivity. I hope this is clear to everyone. Yeah? Perfect. Now comes one more point, guys. That is solubility. That is solubility of ionic compounds. Solubility of ionic compounds in polar solvents. Let's talk about this particular term as well. I'm right now teaching you the basics, right? This is all basics. Solubility of ionic compounds in polar solvents. Try to understand few important things which I'm going to tell you now. This is important also. Okay? Yeah? If you have any issue in understanding any concept, just drag the video a little back. It will be automatically a replay. Okay? All right, guys. So solubility of ionic compounds in polar solvents. Let me make you understand what the term solubility is all about, right? So try to understand what exactly I'm going to say. This is something which is very important. My dear students, imagine that you have got a container over here. You have got a container over here, right? And in this container, for example, there is a polar solvent present. Imagine that there is water present. Imagine that there is water present in the container, right? There is water present in the container. Now, what exactly I'm going to do? I'm going to drop NaCl into water. I'm going to drop NaCl into water. For example, I took one NaCl particle. I'm going to introduce it into water. Now, if you talk about NaCl, you have got Na positive here. You have got Cl negative. So there will be attraction. There will be attraction. My dear students, when you put NaCl into water, what exactly happens? First of all, this force of attraction, it gets broken down. First of all, this force of attraction gets broken down. And when the force of attraction gets broken down, you get Na positive separately and you get Cl negative separately over here. When you get Na positive over here, the negative ends of water, they are going to attack it. Negative ends of water, they are going to get associated with this Na positive. Similarly, the positive ends of water, they are going to get attached with Cl negative over here. Okay? They're going to get attached to this Cl negative over here. So, my dear students, just try to understand few important things over here. First of all, the force of attraction gets broken down over here. And whenever this term comes to our mind, that force of attraction has to be broken down between the ions. One term that comes to my mind, that is lattice energy. Right? Over here, one more term comes into my mind, that is hydration energy. So, whenever we talk about solubility, how many terms are associated with solubility? Two terms. The force of attraction has to be broken down first, right? Number one. Number two, the ion gets hydrated in the second part, okay? My dear students, in the first place, the force of attraction has to be broken down. And in order to break force of attraction, energy is absorbed, right? So the first process in which force of attraction is broken down is that endothermic or exothermic. That is endothermic. The second process in which hydration takes place, hydration is exothermic in nature, right? Hydration is exothermic in nature. Perfect. Perfect, guys. Now understand. When the force of attraction between the ions gets broken down, when the ions get separated, these ions are attacked by the water molecules, right? And there'll be attractions between water molecules and these ions, due to which energy is released. That energy released is something which you call as hydration energy. Oh, my dear students, the energy released due to hydration, is utilized to break the force of attraction between the ions of the upcoming compounds, of the upcoming molecules which you are going to introduce in the container. I hope this is clear to everyone. The energy which is getting released during hydration, that amount of energy is basically utilized in order to break the force of attraction between the ions. Okay? Now, if this entire scenario is clear to you, you had NaCl particle. You introduced NaCl into water. What happened first of all? Force of attraction got broken down. Energy was utilized in that process. Then, when the ions got separated, hydration took place, due to which energy got released. And the energy which is released due to hydration is utilized in order to break the force of attraction in the upcoming ions, which you are going to introduce in the same container. Yeah? Perfect. Now, two things arise over here. Number one, if for example, lattice energy is greater than hydration energy. If lattice energy is greater than hydration energy, lattice energy is the amount of energy which is used to break it. Hydration energy is the amount of energy which is released during hydration. Now you tell me one thing. If lattice energy is greater than hydration energy, should I be calling the process of dissolution? Is the process of dissolution going to be endothermic or exothermic? The overall process of dissolution, is it going to be endothermic or exothermic? Is it going to be endothermic or exothermic? If lattice energy is greater than hydration energy, in the lattice energy is absorbed, so endothermic. Hydration energy is released, so exothermic. If lattice energy is greater than hydration energy, is the dissolution going to be endothermic or exothermic? It is going to be endothermic. The dissolution is going to be endothermic, right? Will the compound be completely soluble in the solvent? The compound won't be completely soluble. The compound won't be completely soluble in the solvent, right? I hope this is clear. I hope this is clear. Number two, you tell me one more thing. If by chance hydration energy is greater than lattice energy, I told you one important thing. Whatever energy is released during hydration, that energy is used to break the force of attraction between the ions of the upcoming molecules which I'm going to put in the container. Yeah? Right? So if hydration energy is greater than lattice energy, just tell me whether the dissolution process is going to be, whether the overall dissolution process is going to be endothermic or exothermic. Over here, it's going to be exothermic, right? And at the same time, I would say the compound is completely soluble. It is completely soluble. It is completely soluble, right? Perfect. Say yes or no in the chat if it is clear. My dear students, one more important thing, which I'm going to tell you now. Solubility of an ionic compound, which we are talking about, it depends on dielectric constant. It depends on dielectric constant of solvent as well. It depends on dielectric constant of solvent as well. Now you must be thinking, oh, how do we define the dielectric constant of solvent? How do we define the dielectric constant of solvent? Let me tell you one simple thing. When we talk about the dielectric constant of solvent, dielectric constant of the solvent, it gives us the idea, about the tendency of solvent to weaken the force of attraction. It gives the idea about the tendency of solvent to weaken the force of attraction. To weaken the force of attraction between the ions. In an ionic compound. Now you tell me one thing. If I have got a solvent which has got more dielectric constant, that solvent which has got more dielectric constant, that will be having more tendency to weaken the force of attraction between the ions of the ionic compound. That will be having more tendency to break the force of attraction between the ions of the ionic compound. So, how do you relate solubility with dielectric constant of solvent? How do you relate solubility with dielectric constant of solvent? So, can I say solubility of an ionic compound is directly proportional to dielectric constant of the solvent? More the dielectric constant of the solvent, more is the tendency of the solvent to to break the force of attraction between the ions of the ionic compound, right? Hence, eventually, more is going to be the solubility. As simple as that, right? Perfect. My dear students, when you talk about water, water has got very high dielectric constant. Water has got very high dielectric constant. Approximately it is 81, right? That's the reason why water is considered to be the universal solvent. That is the reason why we call water as the universal solvent. Its dielectric constant is very high. It has got high tendency to weaken the force of attraction between the ions of the ionic compound, right? That's why majority of the ionic compounds, they are soluble in water, right? That's why we call this water as the universal solvent. Let me know once in the chats if it is super clear to everyone. Quickly, guys. Quickly. Quickly, everyone. So all these points we have already discussed. Have a look. Ionic compounds are more soluble in solvents having high dielectric constants. Water has maximum dielectric constant, approximately 81. Ionic compounds are soluble in water, right? What is the reason? Because of the high dielectric constant of the water. Okay? All right. Now you tell me one thing. Solubility of ionic compound. Solubility of ionic compound. If you want to relate solubility with lattice energy and hydration energy, how you guys are going to do that? Can I say solubility? It is directly proportional to hydration energy and it's inversely proportional to lattice energy. Yeah? Do you agree with this? Solubility of an ionic compound is directly proportional to hydration energy and inversely proportional to lattice energy. If lattice energy of ionic compound is more, that means there'll be strong force of attraction between the ions. It will be difficult to break it. Solubility will be less. Correct? If hydration energy is more, that means more energy is released during hydration. And the amount of energy which is released during hydration, that is utilized to break the force of attraction between the ions. Right? So more the hydration energy, more the solubility. More the lattice energy, lesser the solubility. Remember this particular thing as well. I hope this is super clear to everyone. Say yes or no in the chats if it is clear. Quickly, guys. Quickly, everyone. everyone, quickly. So there are basically two factors which decides the solubility of ionic compound in water, basically, right? One is lattice energy, one is hydration energy. I hope it is clear to everyone. So this was all about your ionic bond and stuff. The actual chemical bonding chapter, in this particular chapter, actually we have to discuss about covalent bonds, right? That is the actual thing which we have to discuss. This is a very small portion, this ionic bond, right? I hope you got all the things, whatever was to be discussed in the ionic bond. The actual thing is covalent bond. So now we are starting the actual chapter. Okay? Now we are starting the actual chapter. My dear students, there are a lot of theories which are given related to covalent compounds, right? The first and the basic theory related to covalent compounds, what is that? That is Lewis theory. And as per your Lewis theory is concerned, which is something which you have studied in your class 8, 9, 10th as well. What is a covalent bond? A covalent bond is formed by the mutual sharing of electrons. Every one of you must be knowing, right? A covalent bond is formed by the mutual sharing of electrons just to complete the octets or duplets. For example, I'm taking a molecule F2 over here. Over here, I'm taking one more molecule O2. Right here, I'm taking one more molecule N2, right? Now, if I ask you, this is, for example, one fluorine atom. This is one more fluorine atom, for example. How many electrons are present in the last shell of fluorine? 7 electrons. 1, 2, 3, 4, 5, 6, and 7. These are what I call as valence electrons of fluorine. Similarly, these are what I call as valence electrons of fluorine. It has got 7 electrons in its outermost shell. So it just needs one electron to complete the octet. Even it just needs one electron to complete the octet. So what exactly they are going to do? They are going to share one electron, right? They are going to contribute one electron. They are going to contribute one electron. One electron is given by one fluorine, another electron is given by another fluorine, right? And this electron pair in the middle, it is mutually shared between two fluorine atoms. It is mutually shared between two fluorine atoms, right? So this is basically the mutual sharing of electrons, and mutual sharing of electron, it leads to the formation of what? It leads to the formation of covalent bond. You should be knowing that. Number one. Number two, have a look. These are the electron pairs of fluorine which belong to the valence shell of fluorine. These are the electron pairs of fluorine which actually belongs to the valence shell of fluorine. But these electron pairs, they do not participate in the bonding. They do not participate in the bonding. And whenever you see such kind of electron pairs which belong to the valence shell but do not participate in the bonding, these electron pairs are what you call as non-bonding electron pairs. Or you call them as the lone pairs. So what are lone pairs? Lone pairs are the electron pairs of the atom which belongs to its valence shell, but they do not participate in the bonding. What do we call this electron pair which is mutually shared? This electron pair which is mutually shared, we call this as bonded pair of electron. We call this as bonded pair of electron. What do we call these three as? These are again three lone pairs of one more fluorine. Okay, right? And my dear students, do remember one simple thing. Whenever a covalent bond is formed, in which both the atoms will contribute one electron. Both the atoms will contribute one electron. Which bond gets formed? It is a single bond which gets formed in between. So this is fluorine. Single bond, fluorine. This is how you are going to represent it. Perfect. This is how you are going to represent it. Yeah. And at the same time, people, the number of electrons contributed by each atom is known as covalency. How many electrons were contributed by this atom and how many electrons were contributed by this atom for bonding, that defines their covalency. Simple again. The number of electrons contributed by each atom for bonding, that defines its covalency. That's all. Similarly, if you talk about O2, for example, I am talking about the structure of O2. I'm talking about the structure of O2. This is one oxygen. This is one more oxygen. Oxygen is a group 16 element. Its outermost shell contains 6 electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Correct? Or let me write this particular electron pair over here. Right? If I ask you, is its octet complete or not? Its octet is not complete. Its octet is not complete. This oxygen should have 8 electrons in its last shell, but it's only having 6. Even this is only having 6. So they will mutually share 2 electrons, right? I mean, this particular oxygen, it will contribute 2 electrons. Even this oxygen will contribute 2 electrons. And these electron pairs will be mutually shared by both. Perfect. And any such bond which is formed by the mutual sharing of electrons, that's something which you call as covalent bond. So over here, again, which bond got formed? It is the covalent bond which got formed, right? Number one. Number two, what do I call this particular electron pair and this particular electron pair? Can you see these two electron pairs? They belong to the valence shell of oxygen, but they did not participate in the bonding. So I'll be calling them as lone pairs. So these are 2 lone pairs of oxygen. Even these are 2 lone pairs of oxygen, right? What are these 2 electron pairs? These 2 electron pairs over here, these are what you call as bonding pair of electrons. So these are what you call as the bonding pair of electrons. I hope it's clear. How many electrons are contributed by this oxygen for bonding? 2. How many electrons are contributed by this oxygen? 2. The number of electrons contributed by each atom, that defines its covalency. So covalency of this oxygen is 2. This is 2. Covalency of this fluorine is 1. This fluorine is 1. I hope it's clear. I hope it's clear. Right? And my dear students, at the same time, whenever each atom contributes 2 electrons, which bond gets formed? It is the double bond which gets formed in between. Right? It is a double bond which gets formed in between. Whenever each atom contributes 2 electrons, right? While the formation of covalent bond, we get a double bond in between. Similarly, triple bond also in case of N2, right? Because 3 electrons will will be contributed by each nitrogen atom. I hope that's clear. Okay. Now, guys, I'm going to show you something interesting. What is that? That is how to draw the structures of different molecules with the help of Lewis concept, right? How do you draw the Lewis structures basically? Okay. There is one simple procedure which you guys have to follow. That's important. Understand properly what I'm going to say. Understand properly what I'm going to say. The first molecule is carbon monoxide. We need to draw its structure, right, as per Lewis theory is concerned. We need to draw its Lewis structure in short. My dear students, the first thing always, what you guys will be doing. If I ask you how many valence electrons are there with carbon, carbon has got 4 valence electrons. Oxygen has got 6 valence electrons. So in total, there are 10 valence electrons. In total, there are 10 valence electrons. My dear students, 10 valence electrons means 5 valence electron pairs. Because 1 electron pair consists of 2 electrons. So 5 valence electron pairs consists of 10 valence electrons. So in total, there are 5 valence electron pairs. Now, see what exactly I'll be doing. This is carbon monoxide. So carbon, this is oxygen. How many valence electron pairs we have? 5. Out of 5 valence electron pairs, I'll put a bond over here, which is made up of 1 electron pair. This is 1 electron pair. I have introduced a bond over here. So out of 5 valence electron pairs, I have utilized 1 over here. I have utilized 1 electron pair. So how many valence electron pairs are left now? Out of 5, 1 is utilized. So 4 are left, right? Now, my dear students, since 4 valence electrons are left, now I'll be trying to complete the octet of these 2 atoms. How exactly? I'll start with more electronegative element. This more electronegative element right here, it has got only 2 electrons. So 4, 2, 4, 6 and 8. Have I completed the octet of this oxygen? Yes, I have completed the octet of this oxygen. Right? Yeah? Is it clear, guys? Is it clear till here? Yeah. Total, we have got 5 valence electron pairs. Out of 5, I have utilized 4. So how many are left? How many are left? 1 electron pair is left, right? That 1 electron pair, I'll keep here. Okay. First of all, check whether the octet of oxygen is complete or not. 2, 4, 6 and 8. Octet of oxygen is complete. Is the octet of carbon complete? Octet of carbon is not complete yet. Check it out. 1, 2, 3 and 4. Carbon has got only 4 electrons, right? What you'll be doing? You'll be removing one of the electron pair from here. Instead of it, you'll put a bond, right? Similarly, remove one more electron pair from here and instead of that electron pair, put a bond. Now check the octet of both these. Check the octet of both these. Have a look about this carbon. 1, 2, 3, 4, 5, 6, 7, 8. Octet of carbon is complete. Look at the octet of oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So octet of both the atoms is complete. Octet of both the atoms is complete. Now, dear students, you got to know the structure of your CO. This is the structure of CO. Now, if I ask you, do you see any charge present on carbon? I can see there is no charge on carbon. I can see there is no charge on oxygen. Now, my dear students, let's actually see, is there any charge on carbon? Is there any charge on oxygen? So basically, I'm asking you about the formal charge. I'm asking you about the formal charge. How do you calculate the formal charge over here? Let me show it to you, formal charge as well. You want to calculate the formal charge of carbon. Tell me, how many valence electrons are there with carbon when carbon is present in non-bonded state, isolated state, isolated. When carbon is isolated, how many valence electrons carbon has? 4, right? Minus. Just tell me one thing. How many electrons this carbon has now in bonded state? 1, 2. Out of these 2, you'll only consider 1. Out of these 2, you'll consider 1. Out of these 2, you'll consider 1. So 1, 2, 3, 4, 5. Number of valence electrons which carbon had in non-bonded state minus number of valence electrons which carbon has in bonded state. So the value comes out to be minus 1. The value comes out to be minus 1. So basically this carbon has got minus 1 charge over here. This carbon has got minus 1 charge over here. Now you must be thinking about the charge present on oxygen as well. Formal charge of oxygen. Tell me one thing. How many valence electrons oxygen has in non-bonded state? 6 minus. How many right now? 1, 2, 3, 4, 5, right? 6 minus 5 comes out to be plus 1. So plus 1 is actually the charge present in oxygen over here, which you call its formal charge. I hope it's clear. Right? So how do you calculate the formal charge now? It's simple. Number of valence electrons in non-bonded state minus number of valence electrons in bonded state. That's it. Yeah? Let me give you a few more examples. Let me give you a few more examples so that it becomes clear to you. NO2 negative. Let's have a look at its structure and then let's talk about its formal charge. Have a look, guys. NO2 negative. First of all, I would want you guys to calculate the valence electrons. I would want you guys to calculate the total number of valence electrons. Nitrogen has got 5 valence electrons. One oxygen atom has got 6. 6 into 2 is 12. There is a negative charge. So add this negative charge. So 12 plus 1, 13. 13 plus 5 is 18. So 18 valence electrons in total. 18 valence electron means how many valence electron pairs? So I'll say 9 valence electron pairs. Now you have to distribute these 9 valence electron pairs in such a way that the octet of all the atom gets completed. Right? So how many atoms are here? 3. Right? 3 atoms. Which one is least electronegative? Nitrogen is least electronegative. The one which is least electronegative has to be the central atom. The one which is the least electronegative, that has to be the central atom. So I'm keeping nitrogen at the center. Right? This is one oxygen. This is one more oxygen. Total 9 valence electron pairs. Out of 9, 1 I'm using here and 1 I'm using here. So out of 9, I have utilized 2. So how many are left? 7 are left. I'm going to fill the octet of the atoms now. I'll start with more electronegative. So let's fill the octet of oxygen. It has got 2, 4, 6, 8. Now talk about this particular oxygen. 2, 4, 6, 8. How many valence electron pairs I had? 9. Out of 9, how many I have used? 1, 2, 3, 4, 5, 6, 7, 8. 1 is left. So that one I'm going to keep over here on nitrogen. Okay. Octet of this particular oxygen is complete. Octet of this oxygen is complete. Is the octet of nitrogen complete? No way. Check it out. 1, 2, 3, 4, 5, 6. It's not complete yet. Now what you'll be doing? You'll be removing one of the lone pairs from any oxygen atom. For example, I'm removing this one. If I remove this lone pair, I have to put a double bond here. Or if you wanted to remove this lone pair, you will have to keep double bond here. Now check the octet of nitrogen over here. 1, 2, 3, 4, 5, 6, 7, 8. Check the octet of this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Right? So this is your NO2 negative. Right? Now, my dear students, it's time to calculate the formal charge. It's time to calculate the formal charge. Look at this particular oxygen. Calculate its formal charge. How many valence electrons are there with oxygen in non-bonded state? 6 minus. In bonded state, how many right now? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 comes out to be minus 1. Right? Look at this particular oxygen. Calculate its formal charge. In normal non-bonded state, 6 valence electrons minus. Right now, 1, 2, 3, 4, 5, and 6. Right? So 6 minus 6 is 0. So this oxygen has got minus 1 of charge, formal charge. This particular oxygen, it does not have any charge. Now look at this nitrogen. Calculate its formal charge. Nitrogen has got 5 valence electrons when in non-bonded state, minus. Right now, how many? 1, 2, 3, 4, and 5. So 5 minus 5 comes out to be 0. So there is no charge present on this nitrogen. Perfect. So formal charge of this particular oxygen is minus 1. Formal charge of this oxygen is 0. And formal charge of this nitrogen is 0 as well. I hope this is clear to everyone. Okay. Let's take one more example. Let's take one more example. Let's take one more example. HCN. Step by step. You have to just remember the steps. Step by step we are doing things. Calculate the total valence electrons. Hydrogen has got 1 valence electron. Carbon has got 4 valence electrons. Nitrogen 5. So 5, 4, 1, 5, 4, 9, 1, 10. So total 10 valence electrons. Right? 10 valence electrons means how many valence electron pairs? I'll say 5 valence electron pairs in total. Right? 5 valence electron pairs in total. Yeah? Perfect. Now guys understand. HCN. HCN. I told you the least electronegative element has to be the central atom. Okay? But in a molecule, if you see hydrogen or fluorine, hydrogen and fluorine, they always should be the terminal atoms. Hydrogen and fluorine, if present in a molecule, they should always be present at the terminal positions, right? So over here we have got hydrogen, so it has to be the terminal one. Now, among carbon and nitrogen, which one is least electronegative? Carbon. So carbon has to be the central atom. This is carbon. This is, for example, hydrogen. This is nitrogen. Okay? Now understand. Total 5 valence electron pairs. Out of 5, this is 1 valence electron pair. This is 1 more. Done. Out of 5, I've utilized 2. Now, start filling the octet of more electronegative element. More electronegative element is nitrogen. It has got right now 2 valence electrons. 4, 6, 8. So the octet of nitrogen is complete. Right? Octet of nitrogen is complete. Total, we had 5 valence electron pairs. Out of 5, how many we have utilized? 1, 2, 3, 4, 5. We have utilized all the 5. But after utilizing all the 5 valence electron pairs, no doubt octet of nitrogen is complete. But is the octet of carbon complete? Check it out. Is the octet of carbon complete? Check it out. 1, 2, 3, 4. No, it's not complete yet. 1, 2, 3, 4. So remove this electron pair and put a double bond here. Now check the octet. 1, 2, 3, 4, 5, 6. It's not complete yet. Remove one more electron pair. Put a bond. Perfect. Now check the octet of carbon. 1, 2, 3, 4, 5, 6, 7, 8. Done. Nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Done. Hydrogen. Its duplet is already completed. Now talk about the formal charges on different atoms. Talk about the formal charges. If I talk about the formal charge of hydrogen, in non-bonded state, hydrogen has got one valence electron. In non-bonded state, minus. Right now, how many valence electrons? Only 1. We have to consider only 1 electron. While calculating the formal charge, from the bond, we have to consider only 1 electron. So 1 minus 1 is 0. So there is no formal charge on this hydrogen. Now talk about the formal charge of this particular carbon over here. Carbon in non-bonded state, 4 valence electrons, minus. Right now, how many? 1, 2, 3, 4. 4 minus 4 is 0. So no formal charge on this carbon. Now talk about nitrogen. In non-bonded state, 5 valence electrons. Right now, 1, 2, 3, 4, 5. In bonded state, 5. 5 minus 5 is 0. So there is no charge present on any of the atoms over here. I hope this is super clear to everyone. Okay? Is it clear, guys? Is it clear quickly? Quickly, let me know in the chats. Yeah? Perfect, guys. So let's have a look on one more example. CO3 dinegative. CO3 dinegative. Let's calculate the valence electrons first. Carbon has got 4 valence electrons. Oxygen has got how many? 6 valence electrons. There are 3 oxygen atoms. So 6 3s that is 18. So let me directly write 4 plus 18. And there is dinegative charge as well. So add them up. Add these 2 electrons up. 18 plus 2 is 20. So 24 valence electrons. 24 valence electron means how many valence electron pairs? I'll say 12 valence electron pairs. Now you have to distribute these 12 valence electron pairs in such a way that the octet of all the atom gets completed, right? So dear students, C and O3. Which one is less electronegative? Carbon. Keep carbon as the central atom. There are 3 oxygen atoms, 1, 2, and 3, right? Now 12 valence electron pairs. I've utilized 1, 2, 3. 3 I have utilized. Now start filling the octet of more electronegative element. So 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. How many valence electron pairs we had? 12. How many we have utilized? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have utilized all the 12 valence electron pairs, right? The octet of oxygen is complete. This oxygen complete. This oxygen complete. Is the octet of carbon complete or not? The octet of carbon is not complete yet. The octet of carbon is not complete yet. Right? Yeah? Right? Octet of carbon is not complete yet. So, try to complete the octet of carbon. What you'll be doing? Carbon right now has got 2, 4, 6. So, take any lone pair out. It is completely your choice. For example, I'm removing this lone pair. And instead of this, I'm keeping a double bond here. Now, check the octet of carbon. 2, 4, 6, 8. 2, 4, 6, 8. So, octet of every single thing is complete. Right? Now, calculate the formal charge of different elements over here. Calculate the formal charge of different elements over here. Formal charge of this oxygen is equal. Oxygen when present in non-bonded state, it has got 6 valence electrons. Right now in the bonded state, 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is equal to minus 1. So its formal charge is minus 1. Right? Look at this particular oxygen. Look at this particular oxygen. Oxygen in non-bonded state, 6 valence electrons minus. Right now in bonded state, 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is equal to minus 1. Look at this particular oxygen. In non-bonded state, 6 valence electrons minus. Right now, how many? Check it out. 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So formal charge on this oxygen is 0. What about the formal charge of carbon? In non-bonded state, 4 valence electrons minus. Right now, 1, 2, 3, 4. So 4 minus 4 is 0. So formal charge of this carbon over here is 0 as well. I hope this again super clear to everyone. Yeah? Perfect. Let's take one more example. Let's take one more example. Now, guys, you have to be quick. I hope you got the concept. It's time to be very quick now to draw the structures and to talk about the formal charges now. See, guys, CO2. CO2, carbon has got 4 valence electron. 6 into 2 is 12. So total 16 valence electrons. That means 8 valence electron pairs, right? Carbon is less electronegative. So in the middle, 1 oxygen, 1 oxygen. 8 valence electrons have used 2. Balance this. 2, 4, 6, 8. 2, 4, 6, and 8. So how many valence electrons we had? 8. Out of 8, how many we have used? 1, 2, 3, 4, 5, 6, 7, 8. All the 8 valence electron pairs we have used. Now, check the octet of carbon. 2, 4. It's not complete. So, remove 1 from here, put a bond. Remove 1 from here and put a bond. Now, check the octet of all the atoms. It will be complete. Okay? Talk about the formal charge. Valence electrons in oxygen in non-bonded state. That's 6 minus. Valence electrons right now. 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So formal charge is 0. Talk about this carbon. Non-bonded state, 4 valence electrons. Bonded state, 1, 2, 3, 4. So 4 minus 4 is 0. Talk about this particular oxygen. Non-bonded state, 6 valence electrons. Minus right now, 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So everything is in front of you. Done and dusted. Yeah? Is it clear to everyone quickly? Is it clear to everyone, people? All clear? Say yes or no in the chats. Say yes or no in the chats. Ozone, one famous molecule this is, right? A lot of questions are asked. No, Hima, you cannot do that. Oxygen is bivalent, right? Oxygen is bivalent. So quickly in the chats, all the things are clear till here? All right, guys. So let's move on then. Let's talk about ozone. See, first of all, what is the first step? Calculate the valence electrons. So 6 3s are 18. So 18 valence electrons in total. So how many valence electron pairs? 9 valence electron pairs, right? So 3 oxygen atoms there are, right? So this is 1, this is 2, this is 3. I'm not talking about the geometry, shape, etc. yet. Okay? Afterwards, we are going to do that. Now check it out. 9 valence electrons, out of which 1 I'm using here, 1 I'm using here. Okay? Now, my dear students, what do you need to do? Complete the octet of the terminal atoms. 2, 4, 6, 8. 2, 4, 6, 8. 9 we had, out of which we have utilized 3, 6 to 8. 8 and 1 is 9. Okay? Now, is the octet of this oxygen complete? It's incomplete right now. 2, 4, and 6. So, what you need to do, just remove one of the lone pair from here and put a double bond. Okay, so 2, 4, 6, and 8. The octet of this oxygen is complete as well. Yeah? Right? Now, my dear students, at the same time, since you got to know the structure of your O3, now let's have a look on the formal charges on different oxygen atoms. Look at this particular oxygen. In non-bonded state, it has got 6 valence electrons minus. In bonded state, how many it has? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 comes out to be minus 1. Look at this particular oxygen. In non-bonded state, it has got 6 valence electrons minus. Right now, it has 1, 2, 3, 4, 5, and 6. So 6 minus 6 is 0. Look at this particular oxygen. In non-bonded state, 6 valence electrons minus, right now, 1, 2, 3, 4, and 5. So 6 minus 5 is plus 1, right? So these are the formal charges present on different oxygen atoms in case of O3. I hope this again clear to everyone. Someone is continuously spamming what is a coordinate bond. I did not talk about coordinate bond yet, just wait for it. Is it clear to everyone, people? Is it clear to everyone quickly? It should be. Yeah? Okay. For example, you have got Cn negative. Can you do it on your own now? Yes, ion, you can remove it from any oxygen atom. Can you do this part on your own now? This is clear, right? All these examples you have seen. It's understood now. It is understood, right? So you can draw its structure, you can talk about the formal charge as well. Now, my dear students, there is something which is very important, from which frequently questions have been asked. What is that? That's Fajan's rules. Before talking about the Fajan's rules, let me talk about few important things. And what are those important things? Let's have a look. So now we are going to discuss the Fajan's rules. Before discussing the Fajan's rules, few points I would like to share with you, right? Let me first of all tell you, no bond is 100% ionic or covalent. There is no bond which can be 100% ionic or covalent. Whenever you see an ionic bond, in the ionic bond, there will be some covalent character. And in the covalent bond, there will be some ionic character. There is no bond which will be 100% ionic or 100% covalent. There will be some covalent character in the ionic bond. There will be some covalent character in the ionic bond. There will be some ionic character in the covalent bond as well. So no bond is 100% covalent or ionic. For example, you have got HF. You have got HF. No doubt there is a covalent bond in between. No doubt there is a covalent bond. But fluorine is more electronegative. So it will attract the bonded pair towards itself, due to which this will be delta negative, this will be delta positive. And due to the presence of these charges, see, this bond was covalent in nature. But due to the presence of these partial charges, it got ionic character as well. So there is ionic character in this particular molecule. There is ionic character in this particular molecule, right? And my dear students, for example, you have got H2. No doubt, on both the sides you have got hydrogen. But my dear students, in this molecule, momentarily, a dipole moment can get induced here. Momentarily, dipole gets induced over here, due to which it also gets the polar character. Due to which it also gets ionic character. So in short, I'm trying to convey, there is no bond which is 100% covalent. There is no bond which is 100% ionic. In every covalent bond, you'll find the ionic character. In every ionic bond, you'll find the covalent character. Point number one, right? Point number one. Point number two, my dear students. What these Fajan's rules tell us basically, they give us the idea about, they let us know how to compare. They let us know how to compare. How to compare covalent character in an ionic bond. So Fajan's rules will let us know which ionic bond has got more covalent character and which ionic bond has got less covalent character. That's something which Fajan's rules are going to let us know, right? It is going to let us know about the covalent character in an ionic compound, in an ionic bond, sorry. Okay, how exactly you'll get the idea in some time. Just I'm telling you the things first of all. Okay, so Fajan's rules will let us know that which ionic bond has got more covalent character and which ionic bond has got less covalent character. That's something which Fajan's rules are going to tell us. Okay, now dear students, there are a few more important things. there are a few more important things which I'm going to discuss with you. And after that, we'll move on to Fajan's rules. Okay? Take a note of one important thing. For example, I have got an atom A. Let's say I've got an atom A, right? Let's assume that there are 7 electrons and 7 protons in this atom A. So this atom is right now electrically neutral. This atom is right now electrically neutral. So right now, can I say 7 protons are holding 7 electrons? Yes, 7 protons are basically holding 7 electrons in atom A. Now imagine that I'm taking 1 electron out. If I take 1 electron out, it gets converted into A positive. Now how many electrons will be here? There will be only 6 electrons. But how many protons will be there? There will be 7 protons there only. By the presence of charge, nothing happens to the protons. Right? By the presence of charge, nothing happens to the protons. Initially, my dear students, 7 protons were holding 7 electrons. Now, the same 7 protons are holding only 6 electrons. Can I say the electrons right here will be experiencing more attraction? The electrons right here will be experiencing more attraction. Right? What does that mean? What does that mean? What does that mean? The electron right here is experiencing more attraction. That means the effective nuclear charge of A positive, is it more or less? It is more than that of the effective nuclear charge of A. So can I say one simple thing? When the parent atom is converted into cation, when the parent atom is converted into cation, its effective nuclear charge increases. And due to increase in the effective nuclear charge, I would say attractive power increases. Attractive power increases. As I told you a few minutes back, 7 protons were holding 7 electrons. Now the same 7 protons are holding 6 electrons. Over here, electrons are experiencing more attraction from the nucleus. Right? That means effective nuclear charge has increased. And effective nuclear charge increase means attractive power has increased. So when you convert the parent atom into cation, so what is happening to the effective nuclear charge? That's increasing. If the effective nuclear charge is increasing, that means the attractive power is increasing. Point number 1. Point number 2. For example, you have got the atom B. Let's assume it has got 7 electrons and 7 protons. Perfect. Right now, it's electrically neutral. Yeah? Now, my dear students, one more important thing. One more important thing. Yes, you can decide on the basis of size as well. I'm not talking in terms of size, anything, right? Leave size part aside. See guys, if you talk about B, for example, I'm giving 1 electron to B. If I give 1 electron to B, it becomes B negative. So initially it had 7 electrons, now it will be having 8 electrons. Protons will be still the same, 7 protons. Initially, 7 protons were holding 7 electrons. But now, same 7 protons are holding 8 electrons. So can I say the force experienced by the electrons here will be comparatively less? What does that mean? That means the effective nuclear charge of B negative will be comparatively less than that of B. So I can simply tell you one important thing. If the effective nuclear charge is decreasing, attractive power, what is happening with the attractive power? Attractive power is decreasing as well. Attractive power is decreasing at the same time. Attractive power is decreasing at the same time. So my dear students, when a parent atom is converted into the anion, attractive power, that decreases. Effective nuclear charge, that decreases. 2 statements which I want every one of you to remember. When the parent atom is converted into cation, effective nuclear charge increases, attractive power increases. When the parent atom is converted into the anion, effective nuclear charge decreases, attractive power decreases. Okay? Right? Yeah? Is it clear? Say yes or no in the chats quickly. Is it clear? Is this particular point clear to you? Is this particular point clear to you? Say yes or no in the chats. I want everyone to say it quickly. Quickly. Everyone means everyone. Quickly in the chats. Then only I can talk about the actual stuff. Quickly, guys. All right, perfect. Now try to understand. Now we are basically going to enter into Fajan's rules. Fajan's rules are going to let us know how to compare covalent character in an ionic bond. Yeah? How to compare covalent character in an ionic bond. Whether an ionic bond has got more covalent character or less covalent character. Fajan's rules is going to let us know about that. Now guys, what is polarization? How do you define the term polarization? It is defined as the distortion of electron cloud. The distortion of electron cloud in simpler words is what we call as polarization. Now what that means? What that means exactly? Let's try to understand. My dear students, imagine that this is the cation over here. Imagine that this is the cation over here. And imagine that this is the anion over here. It is the anion over here, right? Imagine. This is the cation and this is the anion. Perfect. Now, dear students, try to understand few things. Try to understand few things. This is the nucleus of the cation. This is the nucleus of the anion, right? And this part over here, this part over here, this is the electron cloud of anion. This is the electron cloud of anion, right? This is the electron cloud of anion. Dear students, understand, when the cation approaches towards the anion, what happens? When the cation approaches towards the anion, what happens? It is going to, this cation, which carries the positive charge, it is going to attract this electron density towards itself. When the cation approaches towards the anion, what exactly happens? The cation is going to pull the electron cloud towards itself, due to which the electron cloud of anion, which was spherically symmetric, now its shape will get changed. It will slightly shift towards the cation. It will slightly shift towards the cation, right? It will slightly shift towards the cation. So I can say this particular electron cloud, which was spherically symmetric in the beginning, it has got distorted. Its shape has changed. When the cation has approached towards the anion, the cation has attracted the electron cloud of anion towards itself, right? And my dear students, this is something which you call as distortion of electron cloud. This is something which we call as distortion of electron cloud. Electron cloud of anion was spherically symmetric in the starting. Now what happened when the cation approached? When the cation approached, it pulled the electron cloud towards itself. Now do you see some part of electron cloud coming in between the two ions? I say this part of electron cloud is coming in between the two ions, as if this electron cloud is shared by the two ions, right? As if this electron cloud is shared by the ions. So can I say a covalent character is being introduced here? Can I say covalent character is being introduced here? Yeah? Right, guys? Let me tell you, the distortion of electron cloud when the cation approaches the anion. This is something which you call as polarization. And due to polarization, covalent character gets induced in an ionic bond. Covalent character gets induced in an ionic bond. I hope this point is clear to everyone. Due to distortion, due to polarization, how exactly covalent character is induced in an ionic bond? It was supposed to be, this is positive, this is negative. Electrostatic force of attraction. It was supposed to be the ionic bond, and it is the ionic bond. But what happened? When the cation approached, it pulled the electron cloud of anion towards itself, due to which electron cloud shifted in the middle, as if this electron cloud is shared by these two. And sharing is what we call as covalent character, right? So covalent character got induced in this particular bond. Yeah? Perfect. So my dear students, just try to understand one important thing. What is that? When the cation approaches an anion, distortion of electron cloud of anion takes place, and the phenomenon of distortion of electron cloud of anion is something which you call as polarization. And due to polarization, what is happening? Due to polarization, covalent character is induced in an ionic bond. Is this clear? Is this clear, guys? And do remember, covalent character in an ionic bond, that is directly proportional to what? That's directly proportional to the polarization, right? That's directly proportional to the polarization. More the polarization, more the electron cloud in the middle, right? That means more will be the covalent character in the ionic bond. That's all. That's all. So covalent character is directly proportional to polarization. Now, guys, if I talk about the polarization, if I talk about polarization, there are some factors which actually, there are some factors on which this polarization depends upon. Number one, first one is called as polarizing power. Polarizing power, or you call it as the ionic potential as well. And this term, this polarizing power or ionic potential, it is defined only for cations. It is defined only for cations. And how do we define it? How do we define the polarizing power? It is defined as the tendency of the cation to distort the electron density of the anion. The tendency of the cation to distort the electron cloud of the anion. As simple as that. So if I say the cation has got more polarizing power, that means the cation has got more tendency to attract the electron cloud of anion towards itself, due to which what will happen? More polarization will happen. And if more polarization is happening, more will be the covalent character in an ionic bond. I hope you're getting all this. I hope you're getting all this. So I must say, polarizing power of cation, it gives you the idea about the tendency of the cation to distort the electron cloud of anion. So more the polarizing power of cation, in short, more will be the polarization. More will be the polarization. And if polarization is more, I would say the covalent character in an ionic compound will be more. The covalent character in an ionic compound, that's absolutely going to be more. So how polarizing power of cation and covalent character, they are related. So do remember, covalent character in an ionic bond, it's directly proportional to polarizing power of cation. It is directly proportional to polarizing power of cation. This is something which you all must know. Okay? It's directly proportional to polarizing power of cation. Now, the polarizing power of cation, it depends on two things. Polarizing power of cation, it depends on two things. It is directly proportional to charge on cation. It is inversely proportional to size of cation. How can you understand it? It's simple, guys. More the charge on cation, more will be its effective nuclear charge. More effective nuclear charge means more attractive power. More attractive power means more distortion in electron cloud of anion. That means more polarization. That means more covalent character. That's all. Right? Perfect. So polarizing power of cation, that is directly proportional to what? Charge of cation. Yeah? Inversely proportional to size of cation. Lesser the size of cation, more is the positive charge density on cation. More the positive charge density of cation, more is the tendency of cation to pull the electron cloud of anion towards itself. More is the polarization. Hence more is the covalent character. Yeah? Perfect. So polarizing power of cation, it depends on two factors. One is charge of cation and inversely proportional to size of cation. I hope this is clear. Right? And you know, this polarizing power, it's directly proportional to covalent character in an ionic bond. Perfect. I hope this is clear. Arrange the following on the base of the polarizing power. Charge +1, charge +2. More the charge, more the polarizing power of cation. +1, +2, +3. Polarizing power of cation. +2, +4. Polarizing power. +2, +4. +2, +3. Polarizing power. Done? Done? Right? This is simple. Very simple this is. Okay. Arrange the following on the base of polarizing power. Li positive, Na positive, K positive, Rb positive, Cs positive. The charge on every cation is same. Now decide on the basis of size. Lesser the size, more the polarizing power. Lesser the size, more the polarizing power. Right? Lesser the size, more the polarizing power. Okay? Look at this one. Beryllium dye positive, magnesium dye positive, calcium dye positive, strontium dye positive, barium dye positive. Charge everywhere is same. Charge everywhere is same. Decide on the basis of size. Polarizing power and size, inversely proportional. Lesser the size, more the polarizing power. Lesser the size, more the polarizing power. Yeah? Simple and basic. Simple and basic. Perfect? Clear, guys? As I told you a few minutes back, polarizing power, it's also called as ionic potential. And do remember, polarizing power, it also depends on effective nuclear charge in case of what? In case of D block elements. When your cation is a D block element. When your cation is a D block element, you'll be comparing the polarizing power in terms of what? Effective nuclear charge. What does that mean? Have a look, guys, what I'm going to say. Understand. You've got Fe dye positive, cobalt dye positive, nickel dye positive, copper dye positive. Do you know their electron configuration? Fe dye positive configuration. It is 3d6. This is 3d7. This is 3d8. This is 3d9. These are their outermost configurations. This is something which all of you must be knowing. Okay. Now understand one thing. You must have studied about shielding effect. You must have studied about shielding effect, right? If I talk about shielding effect, guys, just tell me one simple thing. Just tell me one simple thing. More the shielding effect of the inner electrons. More the shielding effect of the inner electrons. The force of attraction experienced by the outermost electron. Will that be less or more? More the shielding by the inner electrons. The force of attraction experienced by the outer electron. Will that be less or more? That will be less. If that is less, what does that mean? That means effective nuclear charge. Effective nuclear charge is going to be less. Effective nuclear charge is going to be less. Less effective nuclear charge means less attractive power. Less effective nuclear charge means less attractive power. Something which all of you must be knowing. Understand one more thing. If less is the shielding effect, lesser the shielding effect, if lesser is the shielding effect by inner electrons, more will be the force of attraction on the outer electron. More the force of attraction on the outer electron means more is the effective nuclear charge. More effective nuclear charge means more is the attractive power. More is the attractive power. Right? Now try to understand a few things. You must have studied one simple thing. When you compare the shielding of S, P, D and F, do you remember your D and F electrons, your D and F orbitals, they are considered to be ineffective shielders. They do ineffective shielding. The order of shielding is like this. Have you studied this? S orbitals, they do maximum shielding, followed by P, followed by D, followed by F. D and F they are ineffective shielders. They are ineffective shielders. Do you know? D and F, they are ineffective shielders. Right? See, S has got the maximum shielding power, followed by P. D and F they are ineffective. They do not shield well. They do not shield well. If they do not shield well, the outermost electron will experience more force. Will experience more force of attraction. I hope you are trying to relate it. Now understand how to compare the polarizing power of these ions. This is 3d6, this is 3d7, this is 3d8, this is 3d9. Everywhere electrons are present in D. This is d6, d7, d8, d9. Where are the electrons in D more? Electrons in D are more here. This is D9. More the electrons in D. What is D basically? Is it effective? Is it showing effective shielding or ineffective shielding? D shows ineffective shielding. So more the electrons in D, more will be the ineffective shielding. Just try to understand what I'm saying. Just try to understand what I'm saying. This might be confusing a bit. See, D and F, they show ineffective shielding. More the electrons in D, more the ineffective shielding. More the ineffective shielding. So over here, ineffective shielding will be more. What does that mean? Ineffective shielding is more. Ineffective shielding is more. What does that mean? That means shielding is less. Do you agree with this? Ineffective shielding is more. That actually means shielding is less. And if shielding is less, force of attraction on the outermost electron is more. Z effective is more. So where is Z effective more? Where is Z effective more? In copper dipositive. More Z effective, more attractive power. More attractive power means more is the tendency to distort the electron cloud of anion. More the polarization, more the polarizing power, more the covalent character, everything. Do you agree with all this? Do you agree with all this? Yeah? One more important point. On moving from top to the bottom, when you move from 3D, when you move from 3D to 4D, and then 4D to 5D, what happens to Z effective? Do remember Z effective increases. When you move from 3D to 4D, 4D to 5D, what happens to Z effective? Effective nuclear charge. Effective nuclear charge increases. If effective nuclear charge increases, tell me the order of polarizing power of these ions. My dear students, this is 3D. This belongs to 4D. This belongs to 5D. 3D to 4D, 4D to 5D. Z effective increases. Z effective increases. Attractive power increases. Attractive power increases. Polarizing power increases. So this is the order of polarizing power. Done and dusted, right? Done and dusted. Perfect. Now comes one more point, that is polarizability. That is something which you call as polarizability. See, I told you long back, polarization depends on many factors. One was polarizing power of cation. So till now we were discussing about polarizing power of cation. Now it is the time to discuss polarizability. And polarizability, it is defined for anions. It is defined for anions. How do you define the polarizability? It is basically the tendency of anion to distort its electron cloud. The tendency of anion to distort its electron cloud. Can you imagine what that is? If I say polarizability of anion is more, that means the tendency of anion to distort its electron cloud is more. That means you can easily distort the electron cloud of anion. Right? That means you can easily distort the electron cloud of anion. So first thing, polarizability, it's defined for anions. Number one, it is the tendency of anion. It is the tendency of anion. It is the tendency of anion to get polarized, you can say. It is the tendency of anion to distort its electron cloud. Right? So from now onwards, if I say polarizability of anion is more, that means the anion can easily distort its electron cloud. That means we can easily distort the electron cloud of anion. Right? So do remember, polarizability, it is directly proportional to charge on anion, and it depends on size of anion as well. Okay, now you must be thinking why. See guys, polarizability of anion, it is directly proportional to charge on anion. If more is the charge on anion, anion carries a negative charge. More the charge, more the negative charge on anion, less is going to be Z effective. Less is going to be the attractive power of anion. Less is going to be the attractive power of anion. If less is the attractive power of anion, what does that mean? That means the nucleus of anion is not holding its electron cloud firmly. If nucleus of anion is not holding its electron cloud firmly, can I say the cation can easily distort that? And if cation easily distorts that, I'll say covalent character will be more. polarization will be more, covalent character will be more. So can I say covalent character in an ionic bond, it is directly proportional to polarizability of anion. Polarizability of anion, which is directly proportional to charge on anion, right? More the charge on anion, that means more the negative charge on anion, lesser the Z effective of anion, right? Lesser is the attractive power of anion. So lesser is the tendency of the nucleus of anion to hold its electron cloud. That means easily electron cloud of anion can be distorted, right? That means more can be the polarization. More polarization means more covalent character. At the same time, talk about size of anion as well. More the size of anion, that means more is the electron cloud of anion. Okay? The nucleus won't be holding the electron cloud firmly because the electron cloud is big. If the electron cloud is big, you can easily distort that. If you can easily distort that, what does that mean? That means polarization will be more. And if polarization is more, that means covalent character is more. In short. Let me know once in the chats if all these things are clear. Quickly. So more the charge on anion, less is the effective nuclear charge, more is the polarizability of anion. Yeah? All right. Tell me the polarizability order of these anions. You should be able to tell me that. Tri-negative, di-negative, -1. More the charge on anion, more the polarizability. And more the polarizability, more the tendency of anion to distort its electron cloud. More the polarization, more the covalent character. Right? P tri-negative, S di-negative, Cl negative. The charge on this anion is more. So polarizability is more. If its polarizability is more, the chance to distort its electron cloud is more. That's polarizability. The tendency to distort the electron cloud of anion. If the polarizability of anion is more, that means we can distort the electron cloud of anion easily. That's all. Okay? Let's have a look on few more. Have a look. F negative, Cl negative, Br negative, I negative. The charge on every anion is same. The charge on every anion is same. So you're not going to decide on the basis of charge. Decide on the basis of size. More the size of anion, more the size of anion. That means more is the size of electron cloud of anion. If more is the size of electron cloud of anion, that means the nucleus of anion won't be holding its electron cloud firmly. So that means that electron cloud can be distorted easily. If the electron cloud of anion can be distorted easily, that means polarizability of anion is more, right? So more the size of anion, more is the polarizability. O negative, S negative, size. N tri-negative, P tri-negative, size. More the size, more the polarizability. In short, yeah. Perfect. I hope it is clear. Okay, polarizability order. Polarizability order. P tri-negative, S di-negative, O di-negative. More the charge on anion, more the polarizability. More the polarizability. Let me tell you, O di-negative and I negative, their polarizability is almost same. Their polarizability is almost same. Now I negative, Br negative, Cl negative, F negative. The charge on these is same. Talk in terms of size. More the size of anion, more the polarizability. Right? O di-negative, OH negative. Here it is di-negative. Here it is -1. More the charge on anion, more the polarizability. Right? Now, this is one more case. Have a look on this particular case as well. Which anion can be distorted easily? Which anion has got more polarizability? Understand. The central atom here is arsenic. Here it is phosphorus. Here it's carbon, sulfur, nitrogen. Okay? I'm underlining the central atoms. I'm underlining the central atoms. Among all these central atoms, which central atom is maximum electronegative? Nitrogen is maximum electronegative among all these central atoms. If nitrogen is maximum electronegative, it has got maximum tendency to hold the electron cloud of anion. Right? Nitrogen is maximum electronegative. So it has got maximum tendency to hold the electron cloud of anion. If this nitrogen has got maximum tendency to hold the electron cloud of anion, can the electron cloud of this anion be distorted easily? It won't be distorted easily. it won't be distorted easily. If it is not distorted easily, that means its polarizability is the least among all. Its polarizability is the least among all. I hope you got this as well. Yeah? Perfect. Now guys, since we were talking about polarization, what is polarization? Distortion of electron cloud. Due to polarization, covalent character is induced in an ionic bond. Covalent character is induced in an ionic bond. We know that, right? Perfect. And covalent character in an ionic bond, it depends on polarization. And covalent character, that's inversely proportional to ionic character. Let's try to solve some questions so that you can understand properly. Arrange on the base of covalent character. Arrange on the base of covalent character. Over here, this is zinc dye positive, this is Cl negative. Cadmium dye positive, Cl negative. Hg dye positive, Cl negative. Anion everywhere is same. Anion everywhere is same. This is 3D, this is 4D, this is 5D. 3D to 5D, effective nuclear charge increases. If Z effective increases, polarizing power of cation increases. If polarizing power of cation increases, that means polarization increases. If polarization increases, what does that mean? Covalent character increase in an ionic bond. So this is the order of covalent character. This is the order of covalent character, right? Look at the second one. Zinc dye positive, S dye negative. Cadmium dye positive, S dye negative. Hg dye positive, S dye negative. Now, S dye negative everywhere is same. This is 3D, this is cadmium dye positive is 4D, Hg dye positive is 5D. Again, 5D will have maximum Z effect. Maximum Z effect means more attractive power. More attractive power means it can distort the electron cloud of anion easily. So more will be the polarization, more is the covalent character. In short, this is the order. Yeah? Now you should be easily solving them. This is, the anion everywhere is same. So decide on the basis of cation. Decide on the basis of cation. The charge on cation everywhere is same. Decide on the basis of size. Lesser the size of cation, more is the polarizing power of cation. Lesser the size of cation, more the polarizing power of cation. More the polarizing power of cation, that means more is the covalent character. So this is the order of covalent character, right? Over here, cation is same. Dye positive. This is Be dye positive, okay? This is BeCl2. This is B dye positive, B dye positive, B dye positive. I negative, Br negative, Cl negative, F negative. The charge on every anion is same. So decide on the basis of size of anion. This particular I negative, its size is maximum among all the anions. More the size of anion, more the polarizability of anion. And more the polarizability of anion means more the covalent character. This has to be the covalent character order. I hope it's clear. Right? I hope it's clear. Similarly, tell me the answer of these questions now. Tell me the answer of these questions. This is Al tri positive everywhere. This is F negative, Cl negative, Br negative, I negative. Charge on every anion is same. Decide on the basis of size. More the size of anion, more polarizability. More polarizability means more covalent character. Right? Mg dye positive everywhere same. I negative, Br negative, Cl negative, F negative. More polarizability of anion, more covalent character. Right? Li positive everywhere same. I negative, Br negative, Cl negative, F negative. Polarizability of anion is maximum for I negative. More polarizability means more covalent character. Na positive everywhere same. Again, I negative, Br negative, F negative on the basis of polarizability. Yeah? In all these questions. In all these questions. Now, there is one more point. There is one more point. That particular cation, which has got pseudo inert gas configuration. Pseudo inert gas configuration. Its polarizing power will be more than that of that cation which has got inert gas configuration. Now the point is, what is pseudo inert gas configuration? Pseudo inert gas configuration looks like this. First you have to write the configuration of inert gas. After inert gas, there should be D10 configuration. For example, let's say you have got Cu positive. Let's say you have got Cu positive. And on one more side, you have got Na positive. Okay. What is the configuration of outermost configuration? Okay. What is the configuration of Cu positive? You write it like this. First, you write argon. Then you write 3D10. This is the configuration of Cu positive. Right? What is the configuration of Na positive? Na positive configuration is simple like this. Neon. It was supposed to be 3s1, but it's positive, so it's 3s0. Okay? Right? My dear students, this particular configuration, does it resembles like this? First, you have inert gas, then 3d10 configuration. This particular configuration is something which you call as pseudo inert gas configuration. And that particular cation which has got pseudo inert gas configuration, its pulling power, its attractive power is more. If its attractive power is more, that means its polarizing power will be more. So do remember, among these two cations, which one will have more polarizing power? It is going to be Cu positive, whose polarizing power will be more than that of Na positive. Reason being, the Cu positive has got pseudo inert gas configuration, right? And that particular cation which has got pseudo inert gas configuration, its polarizing power will be always more than that of cation which has got inert gas configuration. This cation has got inert gas configuration. It has got pseudo inert gas configuration. Do remember this particular point as well. Question can be asked. Okay. Few things about Fajan's rules as well. Few applications. Few more applications. My dear students, understand. Ag2S, it is less soluble than Ag2O because covalent character of Ag2S is greater than Ag2O. What does it mean? What does it mean? What does it mean? Do you know like dissolves like? So polar will be dissolved in polar only, right? Polar is dissolved in polar only. Yeah, that's something every one of you will be knowing. Polar is dissolved in polar only. In short, solubility of ionic compound, right? Solubility of ionic compound, or let me write in short as solubility is directly proportional to ionic character. Solubility in polar solvent, it is directly proportional to ionic character. That means it will be inversely proportional to covalent character. What does it mean? See guys, for example, you talk about Ag2S. Let's say you are writing Ag2S, then you have got Ag2O. Look at these two compounds. Ag positive, same. Over here, S di negative, O di negative. Okay. The charge on anion is same, but size of this anion is more. So its polarizability is more, covalent character is more. So where is the covalent character more? Covalent character is more here. Right? Covalent character is inversely proportional to ionic character. So tell me the ionic character order. Ionic character order will be like this. This is the ionic character order. If this is the ionic character order, whatever more the ionic character, more the solubility. So this one has got more ionic character, so this one will have more solubility as well. Right? Solubility order will be like this as well. So which one is more soluble in polar solvent? It's going to be Ag2O, which is more soluble. That means Ag2S, it is less soluble. Okay? The reason being solubility, which is directly proportional to ionic character, inversely proportional to covalent character. Right? A question can be asked like this as well. Number one. Number two. Compare the solubility of FeOH thrice with FeOH twice. Compare the solubility of FeOH thrice with FeOH twice. Over here you have got Fe tri positive, right here you have got Fe di positive. The charge on this cation is more. It has got more polarizing power. More polarizing power means more covalent character. So this is the order of covalent character. So what is the order of ionic character then? What is the order of ionic character? This will be the order of ionic character. This is the order of ionic character. And more the ionic character, more the solubility. So solubility order should be like this. Solubility order should be the same, right? So FeOH whole twice will be more soluble than that of FeOH whole thrice. Or you can say FeOH whole thrice is less soluble than FeOH whole twice. This is one more thing which you have to remember. Question can be asked from this as well. I hope all these things are clear to you. Right? Now, my dear students, one more important thing. Questions are asked about the melting points as well. Melting point order you can give on the basis of Fajan's rules. Okay, have a look. Do remember, melting point of ionic compounds, that is more than that of covalent compounds. melting point of ionic compounds is generally more than that of melting points of covalent compounds. So wherever ionic character is more, melting point will be more. Wherever ionic character is more, melting point is more. Now, if you talk about BeCl2, then you have got MgCl2. Then you have got CaCl2. Beryllium, magnesium, calcium, strontium, barium, right? This is strontium Cl2. And then you have got barium Cl2, right? Now, anion everywhere is same, Cl negative. Look at the cation. B dipositive, Mg dipositive, calcium dipositive, strontium dipositive, right? Cation is different. The charge on cation everywhere is same, dipositive, dipositive. Size is different. That cation which has got lesser size, will have more polarizing power. More polarizing power means more covalent character. So what is the order of covalent character? BeCl2 will have maximum covalent character, followed by GCl2, followed by calcium Cl2, followed by strontium Cl2, followed by barium Cl2. This is the order of covalent character. So what will be the order of ionic character? Ionic character order will be inverse, reverse. This is the order of ionic character, right? And you know, more the ionic character, more the melting point. So which one has got maximum ionic character? This one has got maximum ionic character. So its melting point will be maximum. Yeah, its melting point will be maximum. I hope this is clear. Similarly, talking about thermal stability. First application you saw, the first application of Fajan's rules. What was that? The first application was solubility. Solubility is directly proportional to ionic character. Second was, what was second? Melting point. Melting point is directly proportional to ionic character. Third one is thermal stability. Thermal stability of ionic compounds is more than that of covalent compounds. That means thermal stability that is also directly proportional to ionic character. If it is directly proportional to ionic character, that means inversely proportional to covalent character. Now you decide. Lithium carbonate, then lithium, sodium, potassium, rubidium, cesium. These are the carbonates of group 1. Okay, we have to arrange them on the basis of their thermal stability. Can we do that? We can do that. How exactly? Carbonate, CO3 dinegative, everywhere same. Now cation, Na positive, K positive. This is the cation. The charge on every cation is same. So decide on the basis of size. Lesser the size of cation, more the polarizing power, more the covalent character. So Na2CO3, its covalent character is maximum, followed by K2CO3, followed by Rb2CO3, followed by CS2CO3. This is the covalent character order. That means this has to be the ionic character order. And more the ionic character means more is the thermal stability. So thermal stability of cesium carbonate is going to be maximum among all. Right? Just few things you have to remember. Number 1, solubility directly proportional to ionic character. Number 2, and you know ionic character, that's inversely proportional to covalent character. Number 2, melting point. Solubility inversely proportional to, what am I talking about? Melting point. Okay. Melting point is directly proportional to ionic character. Okay. Number 3, what is that? That is thermal stability. Thermal stability again directly proportional to ionic character. All the things directly proportional to ionic character. Whatever I mentioned over here. Okay. Now guys, let's discuss one more topic, that is dipole moment. But before discussing dipole moment, I think we should take a break. Are you ready for the break? What's the but I want every one of you to be back. Guys, this is the most important chapter and I really do not want you guys to miss it. So it is 8:20 right now. 40. So I'll see you all. So we'll be discussing first dipole moment. After dipole moment, we'll be discussing valence bond theory, then hybridization. Okay, this will be the sequence. Perfect. But you have to be back, guys. And promise that you guys will be back. So till you are not writing promise in the chats, you are not going anywhere. Till you are not writing promise in the chats, you are not going anywhere. Okay, pakka wala promise, yeah. Okay, I'll see you all at 8:45 sharp. Till then, you guys have dinner, or dinner only you'll have. I'll have tea. See you guys in a while, okay? Be back. What's up, guys? Am I again audible, visible to you? Am I again audible, visible to you? Quickly. Yeah? Quickly in the chats. Welcome back, welcome back, welcome back. Quickly let me know in the chats if all of you can hear me. So are you guys done with your dinner and everything? Hello, Prajwal. Is the dinner and stuff done? Odd Explorer. Sir, why you have very less interaction with the students? I just teach, bro. So, ready to start the new topic? Are you all ready? Yes or no in the chats, quickly. With the thumbs ups. I want the Josh back. Josh should not go down. I want all the thumbs ups in the chats, quickly. Yes, Jaswant, you can. Quickly, everyone, everyone. I want the chat rate to go on the higher side. No, I'm not done with my dinner yet. I'll have it after the session. Perfect, perfect, perfect. Guys, I want the chat rate to go really, really high. The Josh has to be back. Perfect. Let's get going now. So let's start the new topic that is again one important topic from which questions are frequently asked. And this particular topic is used in your organic chemistry as well. The topic name is dipole moment. Now, my dear students, what is dipole moment basically? Before talking about the term dipole moment, we should exactly know what a dipole is, right? So what is a dipole? My dear students, whenever you have got two equal and opposite charges, whenever you will see two equal and opposite charges separated by certain distance, the system of equal and opposite charges, the system containing equal and opposite charges separated by certain distance, the system of equal and opposite charges separated by certain distance is something which you call as dipole, Now, my dear students, for a dipole, we define a term dipole moment. For a dipole, we define a term dipole moment. And this dipole moment is represented by this particular symbol, which is pronounced as nu. Dipole moment. How do you define this dipole moment? My dear students, dipole moment is defined as the product of charge and the distance between the charges. Product of charge and distance between the charges. It gives me the value of what? It gives me the value of dipole moment. Well, this particular dipole moment, it is a vector quantity. It is a vector quantity whose direction in chemistry is taken from positive to negative. Whose direction in chemistry is taken from positive to negative. Or you can say from less electronegative element to more electronegative element. Okay. For example, you have got a dipole over here. For this particular dipole, I can define the dipole moment, which is going to be the product of charge and distance over here. And the direction of dipole moment is going to be from positive to negative. This is the direction of dipole moment over here. My dear students, the unit of this particular dipole moment, if you talk about the unit of this particular dipole moment, it's SI unit. SI unit of dipole moment is d by which is represented by D. Okay. For example, I'm taking a molecule over here like HCl. Let's say it's one molecule over here, HCl. Dear students, you know chlorine is more electronegative than that of hydrogen. If chlorine is more electronegative, it's going to attract the bonded pair of electron towards itself, due to which it gets delta negative, it gets delta positive, right? Now you tell me, do we have two equal and opposite charges separated by certain distance? Absolutely. So this particular molecule is behaving like a dipole, right? If I ask you, what will be the direction of dipole moment for this particular molecule? It will be from less electronegative element to more electronegative element, positive to negative. Okay, number one. Number two, I'm writing one particular statement over here. Lone pair also contributes. Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. And let me tell you, its direction is from, or let me write it like this, its direction is taken towards the lone pair. Its direction is taken towards the lone pair. Now, what does it mean? What does this particular statement mean? It's important. Have a look. For example, I'm taking one molecule NH3 over here. NH3. This is one molecule which I've taken over. NH3. My dear students, if I ask you, how many valence electrons nitrogen has? If I ask you, how many valence electrons nitrogen has? You will say it has got 5 valence electrons. 1, 2, 3, 4, and 5. Perfect. Now there are 3 hydrogens over here. So these are 3 hydrogens which are attached to nitrogen. Perfect. These are 3 hydrogens which are attached to nitrogen. Now, my dear students, first of all, if you talk about this particular bond between nitrogen and hydrogen, since we know nitrogen is more electronegative, so it's going to attract the bonded pair towards itself, due to which nitrogen gets delta negative and hydrogen gets delta positive. So, my dear students, this particular bond, is it behaving like the dipole? Yes. So, it will be having definitely a moment whose direction is from positive to negative, right? Similarly, this particular bond, its direction will be positive to negative. This particular one, positive to negative. Now, over here, you have got a lone pair on nitrogen as well. And let me tell you, lone pair also contributes towards the dipole moment. Yeah? Lone pair also contributes towards the dipole moment. And the direction of moment due to lone pair is towards the lone pair. So, how many vectors do we have here? 1, 2, 3, and 4. This is the moment vector due to this particular bond. This is the moment vector due to this particular bond. This is the moment vector due to this particular bond. And this is the moment vector due to the lone pair. So do remember, lone pair also contribute towards the dipole moment. And its direction is taken from, its direction will be always towards the lone pair. As simple as that. Okay, this is one more important statement. Well, after writing this particular statement, there are a few more things which I want to discuss about dipole moment to you. And then I'll make you understand what all these things exactly means. See guys, some important terminology, some important things related to dipole moment. Point number one. The first point is, if the net dipole moment of the molecule comes out to be 0, if the net dipole moment of the molecule comes out to be 0, we call that particular molecule as the non-polar molecule. We call that particular molecule as the non-polar molecule. Point number one. Point number two. If the net dipole moment of the molecule comes out to be non-zero, we call the molecule as the polar molecule. So based on the net dipole moment, we classify molecules into 2 types. Polar molecule, non-polar molecule. If the net dipole moment of the molecule is 0, the molecule is supposed to be non-polar. And if the net dipole moment of the molecule is non-zero, the molecule is supposed to be polar. Let's take certain examples. See guys, for example, I have got BeCl2, okay? If you have a look at the structure of BeCl2, this is Be, this is one chlorine on this side, this is one more chlorine on this side, right? Now, my dear students, if you look at this particular bond between beryllium and chlorine, which one is more electronegative? It is chlorine which is more electronegative. So it will attract the bonded pair towards itself, due to which this particular chlorine will get delta negative and beryllium at the same time will get delta positive. Now talk about this particular bond. Chlorine more electronegative. So this is delta negative, this is delta positive. So my dear students, do you see over here we got two dipoles? This is one dipole, this is one more dipole. Perfect, right? The direction of dipole moment due to this particular dipole, it is from positive to negative. And due to this particular dipole, it's again from positive to negative. So do you see two equal and opposite moments, right? Which get cancelled out over here. So I must say net dipole moment of the molecule is 0. And if the net dipole moment of the molecule is 0, should I be calling this particular molecule as polar or non-polar? So this particular molecule is non-polar. Well, if I ask you, are the bonds polar? The bonds here are polar, but the net dipole moment of the molecule is 0. Bonds here are polar, but the net dipole moment of the molecule is 0. Yeah? The overall molecule is non-polar, but the bonds are polar. I hope this is clear to everyone. Yeah? Perfect. Now, my dear students, one more important thing. For example, you have got carbon dioxide, right? Let's say you have got carbon dioxide. And I'm sure you know the structure of carbon dioxide. This is carbon, this is double bond O, this is double bond O. Now, my dear students, have a look. If you talk about carbon and oxygen, which one is more electronegative? It's oxygen, right? It is oxygen. Do you know oxygen is more electronegative than that of carbon? Absolutely. So bonded pairs will shift towards oxygen, due to which oxygen gets delta negative, carbon gets delta positive. Now, due to this particular bond, again oxygen gets delta negative, carbon gets delta positive. Now, my dear students, over here again we got two dipoles, right? Perfect. So can I say the direction of dipole moment due to this particular dipole is from positive to negative? And similarly over here, it's again going to be positive to negative. So again we have got equal and opposite dipole moments. Again you have got equal and opposite dipole moments, right? So they'll get cancelled out. I would say net dipole moment of the molecule is 0. So this particular molecule overall is supposed to be non-polar. Well, no doubt the bonds are polar, but the overall molecule is non-polar. I hope this is clear, right? Yeah? Perfect. Now, my dear students, one more thing over here. For example, you have got HF, one simple molecule, HF you have. Perfect. Chlorine is more electronegative, so this is delta negative, this is delta positive. So the direction of dipole moment will be in this direction, right? So if I ask you whether the net dipole moment of the molecule is 0 or non-zero, it is non-zero. So this molecule overall is going to be polar in nature, right? The molecule is polar in nature. The overall molecule is polar in nature. Now there are a few shortcuts which I would want you guys to remember for now. I'm going to give you their explanations as well when I'll teach you valence shell electron pair repulsion theory, VSEPR. But right now I want you guys to remember those things first of all. My dear students, there is a particular type of question asked. Whether the molecule is polar or non-polar. Whether the molecule is polar or non-polar. Do remember one important thing which I'm going to tell you. But I'll be explaining that point in VSEPR, not here. But you take a note of it right now. Do remember, whenever you have got a molecule in which the central atom has got no lone pair. In which the central atom has got no lone pair. Number one. Number two, all the terminal atoms are same. All the terminal atoms are same. Number three, the molecule has got regular geometry. The molecule has got regular geometry. Do remember, if a molecule satisfies these three conditions, do remember the net dipole moment of the molecule will be taken as 0 and the molecule is going to be non-polar in nature. For example, whenever you see the molecule of the type AB2L0, AB3L0, AB4L0, AB5L0, AB6L0, L0 means 0 lone pair on the central atom, right? Then you have got AB4L2, then you have got AB2L3. Whenever you see the molecules of these type, do remember, you need not to check anything. You'll directly say these molecules are non-polar in nature. These molecules are non-polar in nature. Their net dipole moment is 0. For example, I'm giving you the molecule like this, CH4. I'm giving you the molecule like this, CH4. I'm giving you the molecule like this, CH4. Now, dear students, if you talk about carbon, how many valence electrons carbon has? Carbon has 4 valence electrons. Carbon is forming 4 bonds. So all the 4 valence electrons are utilized to form 4 sigma bonds. So there'll be no lone pair left on carbon. So no lone pair on carbon. Perfect. How many bonds it is forming? 4 bonds, 4 sigma bonds. So if I ask you about the type of the molecule, let the central atom carbon be represented by A. How many bond pairs it's forming? 4 bond pairs. How many lone pairs carbon has? 0. Is the molecule of the type AB4L0? Yes, molecule is of the type AB4L0. So directly you will say this particular molecule, its net dipole moment is 0 and this molecule is non-polar in nature. Right? Yeah. Perfect. Well, all these things in detail, I'll let you know when I'll be teaching you VSCPR. Right now, I would just want you guys to take a note of these things. That's all. Nothing else. Okay? Perfect? Perfect? Or some of you, they might have studied already VSCPR, right? So let me give you one more example. Anyways, I'll be teaching all this in detail when I'll be teaching VSCPR, okay? For example, you have got molecule like this. For example, you have got SF6. SF6, okay? SF6. Or you have got XeF4. XeF4. Well, my dear students, how many sigma bonds are formed? 6. Sulfur had 6 valence electrons and all the 6 valence electrons are utilized to form 6 sigma bonds. There is no lone pair, right? So let the central atom be A. There are 6 sigma bonds. There is no lone pair. AB6L0 type. So net dipole moment 0, right? Xenon over here, it will be having 2 lone pairs. So 4 sigma bonds, 2 lone pairs of the type AB4L2. Again, AB4L2 comes in this category, right? Its net dipole moment will be 0. So it's going to be again non-polar in nature. Yeah? Perfect. I hope this is clear. Now, let's try to do certain questions so that all these things, they properly become clear to you. Okay? Have a look. Let's start with the third question. You have got HF, HCl, HBr, HI, right? Okay. My dear students, look at the electronegativity difference between hydrogen and fluorine. Can I say the electronegativity difference between fluorine and hydrogen is more than that of the electronegativity difference between hydrogen and chlorine? Right? If the electronegativity difference between H and F is more, that means more charges will be on the atoms. And more the charges means more the dipole moment. So the dipole moment order is going to be this. Simple. You just have to check the electronegativity difference. Wherever the electronegativity difference is more, dipole moment is going to be more. Except certain cases which I'll let you know. Okay. Look at the second one. Carbon attached with chlorine. Chlorine is more electronegative. It will attract the bonded pair. So delta negative, delta positive. Look at this one. Delta negative, delta positive. Dipole, dipole. Dipole moment direction in this way, dipole moment direction in this way. So you have got 2 bond moments over here. So net dipole moment. This is a vector, this is a vector. Going in the same direction. So net dipole moment will be in this way. Perfect. Net dipole moment is going to be in this way. Look at the other one. TCl. Delta negative, delta positive. So again, dipole moment direction, right? This is going to be delta negative, delta positive. Dipole moment direction. Equal and opposite bond moments over here. They'll cancel out. So net dipole moment of this molecule over here is going to be 0, right? So among these two molecules, which one has got more dipole moment? It's going to be the first one. The second one has got zero dipole moment. Yeah? Simple. Look at the first one, NH3 and NF3. So let me write NH3 over here and let's compare its dipole moment with NF3. So my dear students, first of all, nitrogen, it's attached to 3 hydrogen atoms. It is attached to 3 hydrogen atoms, and on nitrogen there is a lone pair. Similarly, this is NF3. Nitrogen, it's attached to 3 fluorine atoms, and on nitrogen there is a lone pair. Right? Now, my dear students, lone pair also contributes towards the dipole moment, and its direction is towards the dipole moment. Its direction is towards the dipole moment. Now look at this particular bond, nitrogen, hydrogen. Nitrogen is more electronegative, so it will attract the bonded pair, delta negative, delta positive. So due to this particular bond, it is going to be this way. Due to this particular bond, in this way. Due to this particular bond, in this way. Perfect. Now look at nitrogen-fluorine bond. Fluorine is more electronegative. So fluorine will attract the bonded pair towards itself, due to which fluorine gets delta negative, nitrogen gets delta positive. So positive to negative, positive to negative, positive to negative. My dear students, just have a look carefully. All these 4 bond moments, they are almost in similar direction. They're almost in same direction. But over here, one is going upwards and other 3, they are diverging downwards. So where will cancellation of bond moments happen? What are these bond moments? These are vectors basically. So can I say cancellation of vectors will take place here in this scenario? And in this particular scenario, no cancellation is going to take place. All the vectors are pointing almost in the similar direction. And over here, 3 vectors are pointing almost downwards and 1 vector is pointing upwards. So cancellation of vectors will take place here. So where will be the net dipole moment more? Net dipole moment will be more in case of NH3, because there is no cancellation of bond moments in NH3, whereas there is cancellation, there is some cancellation of bond moments in NF3. I hope this is clear to everyone. Yeah? If this is clear to everyone, let's have a look on one more. Let's have a look on one more question. Now, my dear students, understand properly. I'm sure every one of you would have studied vectors properly. Yeah? Right? Rajwal, I'm teaching you bonding right now. I'm teaching you something dipole moment and you're asking me isomers. Oh, this is irrelevant. All right. My dear students, look at these 2 molecules. These 3 molecules over here. CH3. This is CH3. Now you tell me, CH3, whether it is electron donating or electron withdrawing. CH3 is electron donating. So this CH3, it will push the electron density towards the ring. It is electron donating. It will push the electron density towards the ring. If it is pushing the electron density, it will get delta positive. Over here, you can write delta negative. So the direction is from positive to negative. Over here, the direction is from positive to negative. Equal and opposite bond moments, net dipole moment is 0. Net dipole moment in this particular case is going to be 0. Perfect. Look at the second one. Electron donating. They'll push the electron density, right? Positive, negative. So bond moment direction in this way, bond moment direction in this way. Now, my dear students, you can shift the vectors as well, just to get the resultant. One vector is pointing downwards. One vector is pointing downwards. One vector is pointing downwards, right? Another vector is pointing in this way. What is the angle between them? Angle between them is 120. Angle between them is 120, right? Now look at this one. This is positive, negative, right? Positive, negative, right? Shift the vectors. If I write this particular vector over here and this particular vector in this direction, the angle between them is 60. Do you know, smaller the angle between the vectors, maximum will be the resultant, right? Smaller the angle between the vectors, more will be their resultant. So over here, the net dipole moment is 0. Now among these 2, where will be the resultant more? Wherever angle is less, resultant is going to be more. So I would say 3 is going to have maximum dipole moment, followed by 2, followed by 1. I hope this is clear. I hope this is clear. Right? Now look at the other example. CH3, it is electron donating. NO2, it is electron withdrawing. Okay? If CH3 is electron donating, it will push the electron density in the ring. So it will get delta positive and over here delta negative. So vector will be in this direction, positive, negative. Now NO2 is electron withdrawing. It will withdraw the electrons. So it will get delta negative, here delta positive. So positive to negative. Now shift the vectors. One vector is pointing downwards. Another vector is pointing in this way. Perfect. What is the angle between them? Angle between them is 120. Perfect. Now look at the next example. This is positive to negative, right? This is positive to negative. Shift the vectors. One vector is pointing downwards. Another vector is pointing in this way. So angle between them is 60, right? Look at this one. Positive to negative. And this positive to negative. Both the vectors are pointing downwards, right? Angle over here is 0. Angle over here is 0 degree, right? Smaller the angle between the vectors, more is going to be the resultant. Where is the resultant maximum here? I'll say at 3 resultant will be maximum, followed by 2, followed by 1. So net dipole moment is going to be maximum in 3, followed by 2, followed by 1. I hope this is clear again to everyone. Yeah? Perfectly done? If this is perfectly done, what do you think about these examples? In the example number first over here, do not get confused. Do not get confused in the example number 7 over here. Normally, if you see, just a second, guys. Just a second. Just a second. Okay. Okay, let me write it over here. You have got CH3F. You have got CH3Cl. You have got CH3Br. You have got CH3I. Perfect. These are few molecules which I have mentioned over here. Yeah? These are few molecules which I have mentioned over here. Now understand. Understand properly. CH3F. That means this carbon is attached with 3 hydrogens and 1 fluorine. So there is a bond between carbon and fluorine. There is a bond between carbon and chlorine. There is a bond between carbon and bromine. There is a bond between carbon and iodine. Right? Now, my dear students, what do you think? Electronegativity difference between carbon and fluorine is more than that of electronegativity difference between carbon and chlorine, due to which the charges on carbon and fluorine will be more than that of charges on carbon and chlorine. And more the charges means more the dipole moment. So as per the charge factor is concerned, this has to be the dipole moment order. This has to be the dipole moment order. As per the charge factor is concerned, this has to be the dipole moment order. But if you remember, dipole moment, how did we define? It is the product of charge and distance. More the charge, more the dipole moment. But distance also is there, right? And this is the case where distance dominates over charge. Now, as per distance factor, let's see what should be the dipole moment. More the distance, more the dipole moment. See, the distance between C and F is less than that of the distance between C and Cl. So if I compare these two molecules, as per distance, distance between C and Cl is more than that of distance between C and F. So what is the order as per distance? Order as per distance is 2 should have more dipole moment than 1. As per charge factor, 1 should have more dipole moment than 2. As per distance factor, 2 should have more dipole moment than that of 1. And this is the case wherein distance dominates over charge. Distance factor dominates over the charge factor. And eventually, after seeing both, what is the final order of the dipole moments? The dipole moment order is going to be 2, then 1, then 3, then 4. This is the actual order of the dipole moments over here. I hope this is clear to everyone. Yeah? Yeah? Perfect. And this is the only question wherein you have to see the distance factor. All the other questions, you will see the charge factor. You will see the electronegativity difference factor. More the electronegativity difference, more is going to be the dipole moment in all the other cases. I hope this is clear, right? Okay, for example, you have got H2O and H2S. Where do you see the dipole moment more? H2O or H2S? Quickly. The bond is between O and H. The bond is between S and H. Electronegativity difference between oxygen and hydrogen is more than that of electronegativity difference between hydrogen and sulfur. More the electronegativity difference, that means more is the charges on the atoms, and hence more is going to be the dipole moment. I hope this is clear. Right? Okay. NH3PH3. NH3PH3. Nitrogen and hydrogen. Phosphorus and hydrogen. Electronegativity difference between nitrogen and hydrogen is more than that of phosphorus and hydrogen. So more the electronegativity difference, more is going to be the dipole moment. I hope this is clear. Then you have got H2O and NH3. H2O and NH3. Tell me, where is the dipole moment more? Quickly in the chats. The bond is between oxygen and hydrogen. The bond is between nitrogen and hydrogen. Oxygen-hydrogen electronegativity difference is more than that of nitrogen and hydrogen. Due to which, this is going to be the dipole moment. Perfect. And my dear students, one last question. H2O and HF. H2O and HF. The bond is between oxygen and hydrogen. Okay. Here the bond is between hydrogen and fluorine. So electronegativity difference between H and F is more. So this should be the dipole moment order. But as per your NCERT, NCERT mentions it like this. NCERT mentions it like this. So you have to remember this order only. Actually, HF should have more dipole moment than that of H2O. Right? That's the actual molecule. That's the actual answer. HF should have more dipole moment than that of H2O. But your NCERT mentions H2O to have more dipole moment than that of HF. So you are going to remember it directly. Right? You are going to remember it directly. Perfect. I hope this is clear to everyone. Yeah? Okay. Look at this question. Look at this question, guys. Let's try to solve this. These are 4 molecules which are given. 1, 2, 3, and 4. We have to arrange them on the basis of their dipole moments. What do you think? What do you think? Quickly, what do you think? Understand. Chlorine is electronegative. Then that of chlorine. It is electron withdrawing. So it will withdraw the electrons. So fluorine will get delta negative. This carbon will get delta positive. So the bond moment direction is in this way. Right? Let's assume the magnitude of this vector is x. Let's assume the magnitude of this vector is x. Right? Similarly, magnitude of this vector will be also x. And magnitude of this particular vector, it's also going to be x. Now, my dear students, if you look at this particular vector and this particular vector, what is the angle between the two? This is one vector whose magnitude is x. This is one more vector whose magnitude is also x. So, 2 vectors at an angle of 120. That means the resultant should be in this direction. And 2 vectors of equal magnitude at an angle of 120. The resultant is also x. So resultant of this particular vector and this particular vector will be in this way, which will be whose magnitude will be also x. So in the same direction, you have now x and x. So the net dipole moment, its magnitude will be 2x. Its magnitude will be 2x, right? Look at this one. This is x, for example. This is x. And this is x. I'm just writing positive to negative, okay? Positive to negative. Now, my dear students, understand. This particular vector is upwards. This particular vector in this way. So these two are same. These two are the vectors of equal magnitude at an angle of 120. So the resultant has to be in this direction. At an angle of 120 means that means the resultant magnitude should be also x. Now this is x. This is x. They'll cancel out. So I would say the net dipole moment of this particular molecule has to be 0. Simple. Now, my dear students, look at this one. Positive to negative, positive to negative, positive to negative. So this one directly gets cut and net dipole moment is going to be x. Perfect. Look at the last one. Positive to negative, positive to negative. If this is x, this is also x, cancelled out. So net dipole moment of this molecule is also 0. Perfect. Now arrange them. Arrange them, my dear students. Arrange them. So we have got how many molecules with 0 dipole moment? Second and 4. Second and 4 have got 0. Which molecule has got maximum? First molecule has got maximum, followed by third. Then you have got 2 and 4, which have got 0 dipole moments. So this is the order of the net dipole moment for this particular question if it is asked. I hope this is clear to everyone. I hope this is clear to everyone. Yeah? Okay. One more question I'm giving you. Let me see if you can solve this one or not. See, guys. This is chlorine on this side, chlorine on this side. Let me know in the chats whether the net dipole moment of this molecule is 0 or not. Quickly. Quickly. Quickly, guys. Okay, look at the first one. Chlorine, more electron withdrawing, right? So delta negative, delta positive in this way. Over here in this way, cancelled out. So net dipole moment of this particular molecule will be 0, right? Look at this one. No doubt, OH, OH, OH and OH. Now you must be thinking, since two OH groups are at position 1 and 4, right? So they should cancel and its net dipole moment should be 0 as well. But that's not the case. This particular molecule, its net dipole moment is non-zero. Even this particular molecule, its net dipole moment also is non-zero, right? For example, if this is the structure, O and H, look at this bond, O and H. Oxygen is more electronegative. So delta negative, delta positive. In this way, delta negative, delta positive. In this way, do you see these two cancelling? These two are not cancelling each other. So net dipole moment of this molecule has to be non-zero. Even this one, S and H, they won't cancel. So net dipole moment has to be non-zero. So these things you have to remember, my dear students. These things you have to remember. Whenever you talk about dipole moments, these are few examples which you have to take into consideration. Okay? Perfect. The question which was asked in NEET 2020, what do you think about this one? What do you think about this one? Which of the following set of molecules will have zero dipole moments? Zero dipole moments. Quickly. Quickly, guys. Over here, you have got hydrogen fluoride, HF. HF does not have zero dipole moment, so this cannot be the answer. Right? NF3. We saw NF3 few minutes back. It has got net dipole moment, so this cannot be the answer. Ammonia, NH3. NH3 has got dipole moment. We saw it few minutes back. This cannot be the answer. Right? So option C is the one which is correct. Yeah? This sort of equation you should be able to solve from now onwards. I hope all this is clear to you. Even if you want to have a look at their structures, you can check it out. These are the structures from which you can easily tell. See, guys, this is one moment at an angle of 120. So resulted in this way. So resulted in this way. So this and this get cancelled. Net dipole moment is 0. And everywhere net dipole moment is 0. So these are the molecules whose net dipole moment is 0 basically. Okay. Perfect. Now, my dear students, let's start with one of the most important theories of the chapter, that is valence bond theory. So what all things this valence bond theory tells us? First of all, whatever I've taught till now, is every single thing clear? Whatever I've taught, I've started everything from basics itself, right? As if you have never studied the chapter before. So you tell me in the chats whether every single thing is clear till here or not. Let me know quickly in the chats with the thumbs ups at least. Quickly. I want everyone to say it. Everyone, quickly. Quickly, guys. All right, people. So let's move on then. Let's get going. Let's start with something called as valence bond theory. One important theory this is, okay? So understand it properly. So first of all, what kind of information this theory gives us? My dear students, let me tell you, valence bond theory, it explains the formation of covalent bond. Valence bond theory is going to let you know how exactly covalent bond is formed. Valence bond theory is going to let you know how exactly covalent bond is formed between two atoms, right? Now, as far as this particular theory is concerned, the first important point of this theory, a covalent bond is formed by the overlap of atomic orbitals of the bonding atoms. In order to show the overlap, the bonding atoms must come close such that their orbitals can overlap. My dear students, understand. Whenever a bond has to be formed between two atoms, let's say this one atom, this one more atom, a bond has to be formed, a covalent bond has to be formed between these two atoms. First of all, in order to form a covalent bond, the bonding atoms, they must approach each other. They must come closer. Why should they come closer? So that their atomic orbitals, they can penetrate into each other. And let me tell you, penetration of atomic orbitals of bonding atoms into each other, that is something which you call as overlapping. So what is overlapping? Overlapping is simply defined as the penetration. It is simply defining as the penetration of atomic orbitals of bonding atoms into each other. This is something which you call as overlapping. Now, this overlap we have to discuss in detail. I just gave you the idea of what overlap is. So, just one thing which you have to remember. Whenever a covalent bond has to be formed between two atoms, two bonding atoms, they should approach each other, they should come closer so that their atomic orbitals will merge into each other, so that their atomic orbitals will penetrate into each other, and penetration of atomic orbitals of bonding atoms into each other, that's something which you call as overlap. That's something which we call as overlap. And my dear students, what this theory says, a covalent bond is formed by the overlap of atomic orbitals into each other. So whenever you see atomic orbitals of two bonding atoms overlapping, just remember, covalent bond will be formed at that point of time. Due to overlapping only, covalent bond is formed, as per this particular theory, right? As per this particular theory. And in order to show overlap, the bonding atoms should come closer. Now, my dear students, for example, if I talk about the bonding atoms, let's say this is one bonding atom whose nucleus is this. And this is the electron, for example, of this particular bonding atom. Let's say you have got one more bonding atom whose nucleus is this. And this is the electron of this particular bonding atom. Now, in order to form a bond, they should come closer so that their atomic orbitals will penetrate into each other, right? But before talking about that, let me tell you, when these bonding atoms will approach each other, let's exactly get to know what kind of forces will exist between the two. Let's see what kind of forces arise when these two bonding atoms will approach each other. My dear students, first of all, this is the electron. Can I say there is force of attraction between the nucleus and this particular electron in this direction? You know it. Similarly, this particular nucleus, it will be pulling its electron towards itself, right? Perfect. Can I say at the same time, this particular nucleus will be attracting this particular electron towards itself? Absolutely. This particular nucleus, it will be attracting this particular electron towards itself? Absolutely. Yeah. Right? Now, dear students, one more thing. This is the nucleus, this is the nucleus. Can I say there will be repulsions between these two nucleus as well? Right? Like charges, repulsions. Electron, repulsion as well. So can I say when the atoms approach towards each other, two types of forces they come into play. Attractive forces and repulsive forces. Two types of forces come into play. One is attractive forces, another one is repulsive forces. Attractive and repulsive forces. When the atoms approach each other, two types of forces arise, attractive and repulsive. My dear students, few things I would want to tell you. Attractive forces, they try to increase the stability of the system. They try to increase the stability of the system. Attractive forces, they stabilize the system. Repulsive forces, they destabilize the system. They destabilize the system. Why is that? Why is that? One thing which every one of you must be knowing. Stability is inversely proportional to energy. More the energy possessed by the system, lesser is going to be the stability. Less the energy possessed by the system, more is going to be the stability. So, lesser the energy in the system, more stability. More energy in the system, less stability. Now, I have already mentioned one thing before. Due to attractions, energy is released. Due to attractions, energy is released. My dear students, due to attractions, energy is released. If energy is released, the system will be having less energy after the release of energy. And if the system has less energy, its stability will be more. So I'll categorically say attractive forces, they try to stabilize the system. Whereas if I talk about repulsive forces, due to attractions, energy is released, the energy possessed by the system becomes low, due to which stability increases, right? If I'm releasing energy, so the amount of energy with me, that decreases with time, correct? Simple. And due to repulsions, energy of the system increases. And if the energy of the system increases, stability decreases. So attractive forces, they stabilize the system. Repulsive forces, they destabilize the system. Point number one. Point number two, my dear students, which I would want to share with you. What is that? Let's have a look. Understand. For example, I have got two atoms. These are two atoms right now, okay? And I'm assuming that these two atoms are right now at infinite distance apart. Let me tell you, when the atoms will be at infinite distance apart, force of attraction between them will be zero, right? So right now the atoms are at infinite distance apart. So force of attraction between them must be zero. Now guys, when these atoms will start coming closer, what will happen? Distance between them will decrease. If the distance is decreasing, that means force of attraction will be increasing. Imagine that this is a positive charge, this is a negative charge. Imagine that as if this is positive charge, this is negative charge, right? They are initially at infinite distance apart. Force of attraction between them has to be zero, right? Now, they start approaching towards each other. Distance between them is decreasing. Force of attraction is increasing. Force of attraction is increasing. Force of attraction is increasing. There will be a scenario when the atoms will be at maximum closest distance. There will be a scenario when the atoms will be at maximum closest distance. And when the atoms will be at maximum closest distance, at that point of time, force of attraction between the atoms will be maximum. Force of attraction between the atoms will be maximum. And at that point of time, whatever is the distance from the center of one atom to the center of another atom, that distance is something which you call as bond length. So over here, basically a molecule has got formed. That's why the force of attraction between the atoms right here is maximum, right? So the distance between their centers is going to be the bond length. Perfect? Right? I hope this is clear. Guys, who is this? Who are these people who are spamming? Let me just block them just a second. This one is gone. Who was this? Rao Saab, who is this? No. Gone. They are done and dusted. Okay. Perfect. So I hope you got this particular point. When the atoms were at infinite distance apart, force of attraction between them was zero. Now the atoms are coming closer. Distance between them is decreasing. Force of attraction is increasing. Now there will be a scenario when the atoms will be at maximum closest distance. At that point of time, force of attraction between them will be maximum, right? That means a molecule has got formed over here. Initially the atoms were far. Now they are coming closer. Over here, molecule has got formed, right? Force of attraction between the atoms is maximum. And the distance between them is something which I call as bond length. My dear students, just tell me one thing, one important thing. If I want these atoms to come a little more closer, do remember, repulsive forces will start there. So, can I simply generalize a statement that attractive forces attractive forces, they are long range forces. Attractive forces, they are long range forces, right? They arise at greater distances. Whereas if I talk about repulsive forces are short range forces. Repulsive forces are short range forces. Repulsive forces are short range forces, right? Repulsive forces arise when the distance is very, very, very small. Attractive forces arise when the distance is large, right? So repulsive forces, they are short range forces, whereas attractive forces, they are long range forces. Attractive forces exist at larger distances. Repulsive forces exist at very smaller distance. I hope this is clear. Now, if this is clear to everyone, let's try to analyze and understand a graph over here. But before talking about the graph, this is the point. When the atoms approach, two types of forces will arise. One is attractive force, one is repulsive force. Due to attractive force, what happens? Attractive force stabilizes the system, right? Increase the stability of the system, right? Whereas repulsive forces, they decreases the stability of the system. And stability, that's inversely proportional to energy, you know it. Perfect. And attractive forces are long range, whereas repulsive forces are short range. Perfect. If it is clear, then there is one graph which is really, really very important. What is that? That is the graph between potential energy and internuclear distance. Try to understand this particular graph. This is important, guys. You have to understand this. You have to understand this particular graph. Okay? See. Try to understand this particular curve carefully. What is happening to this here? Okay. This y-axis, it represents the potential energy of the system. Potential energy of the system, which I'm representing with U. And this particular axis, it represents internuclear distance, which is represented by R. Internuclear distance, which is represented by R. Try to understand what exactly I'm going to say. My dear students, just one thing which you need to analyze over here. What is that particular thing? If I start from this particular point, what are the coordinates of this point? This is the origin basically. This is the origin. Its coordinates are 0, 0, right? So R value over here is 0. R value is tending towards 0, right? So the distance between the atoms is tending towards 0. That means atoms are very, very, very close. When you move far, that means R value is increasing. Internuclear distance between the atoms, that's increasing. That's increasing. That's increasing, right? So over here somewhere, can I say there will be R tending towards infinity also? Somewhere there will be R tending towards infinity. That means that point will represent when the atoms are at infinite distance apart. I'm assuming the atoms are at infinite distance apart. So I'm starting from here somewhere, right? Atoms are at infinite distance apart. And you know, when the atoms are at infinite distance apart, force of attraction between them is 0. Force of attraction between them is 0. Now, come from right to left. If you are coming from right to left in this direction, R values decreasing. That means if R is decreasing, internuclear distance is decreasing. That means atoms are coming closer. If atoms are coming closer, distance between them is decreasing. Force of attraction is increasing. Energy is released. Energy with them, that decrease with time. That decrease with time. Right? If you move from positive towards negative, if you move from right to left, that means R value is decreasing. Atoms are coming closer. Distance between them is decreasing. Force of attraction is increasing. If the force of attraction is increasing, energy is continuously released by the system. So energy possessed by the system, that decrease with time. So energy possessed by the system, that decrease with time. So it is decreasing with time. Energy possessed by the system, that is decreasing with time. Correct? For example, this is the minimum value of energy of the system. This is the minimum value of energy of the system. Minimum value of energy of the system means the system is maximum stable. Minimum value of energy means the system is maximum stable. When is the system maximum stable? When the force of attraction between the atoms will be maximum. So this is the point. at which the force of attraction between the atoms is maximum. That means the atoms are right now at maximum closest distance. The atoms are right now at maximum closest distance, which tells you that the force of attraction between the atoms is maximum. And whatever is the distance at this point, whatever is the distance between the two, between the nuclei of these two atoms, that's something which you call as bond length. Perfect? That's something which you call as bond length. Now, my dear students, if you want these atoms to go a little more closer, what will happen? Repulsive force will increase. And repulsive forces, what do? They tend to increase the energy of the system. So if I want these atoms to come a little more closer, if I move further in this direction, if I decrease the value of R a bit further, that means I want these atoms to come closer. So distance between them is decreasing, but now repulsive force will start, and repulsive forces will tend to increase the energy of the system. So this is how the graph looks like. This is the minimum value of energy. And at the minimum value of energy, the system is considered to be maximum stable. The system is considered to be maximum stable. I hope this is clear to everyone. At the same time, my dear students, the distance from here to here is something which you call as bond energy. Perfect? It's called as bond energy. The amount of energy which is needed to break 1 mole of bonds, basically. That's something which I'll discuss afterwards. Leave that part aside. Yeah? Over here, we have got one important point to discuss. What is that? At this particular point, if I want you guys to draw a tangent, can you draw a tangent at this point? Yes, you can. This is the tangent, right? If I ask you, what is the slope of the tangent at this point? Slope of the tangent at this point is 0, basically, right? Slope of the tangent at this point is 0. How can we represent that mathematically? Slope of the tangent at a point that is represented by dy by dx. But along y-axis, you have got u. Along x-axis, you have got r. Can I say at this particular point, du by dr value is coming out to be 0? What does that mean? That means the slope of tangent at a point on potential energy versus internuclear distance curve, right? So at this particular point, when the energy of the system is minimum, right? When the molecule formation has taken place, when the force of attraction between the atoms is maximum, right? When the distance between the atoms is what we call as bond length, at this particular point, du by dr, this value has to be 0, right? At this particular point, du by dr value has to be 0. Now, my dear students, if you got to know this particular point, how can we relate it with the questions? How can we relate it with the questions? I'm going to give you one question so that you can understand and analyze it properly. See, one simple question I'm giving you. The variation of potential energy with R between two atoms A and B. This is the variation of potential energy with R. Calculate the bond length. Calculate the bond length. My dear students, when we need to calculate bond length, at the point of bond length, that means atoms are at maximum closest distance. Energy of the system is minimum. At that point, du by dr value has to be 0, right? So I got to know one important thing. Du divided by dr value has to be 0. Then only I can calculate the bond length, right? Perfect. Now guys, understand. Du by dr. That means you have to differentiate this u with respect to r. Now differentiate it. Differentiate this u with respect to r. So I'll be writing du divided by dr. Du by dr will be equal to, it is basically going to be 6r raised power minus 2, or let me write it like this first of all, just a second. Ur is equal to, it is 6r raised power minus 2 plus 3r plus 2. Correct? Now differentiate it. Du divided by dr is equal to, it's going to be 6 as such, x raised power n is x nx n minus 1, right? So it's going to be minus 12 r raised power minus 3 plus this is going to be 3, that's it. Now du by dr value, this has to be 0. So I would say minus 12 r raised power minus 3 is equal to minus 3. So minus minus cancel. If minus minus cancel, you got to know r raised power minus 3 is equal to 3 divided by 12. 3 divided by 12 is 1 by 4. So r raised power minus 3 is equal to 1 by 4. Perfect. R raised power minus 3 is equal to 1 by 4. right? So that's it. You can get the value of R from here. Correct? Perfect. So my dear students, the final answer of this particular question, that is done now, right? That is done. So this R, can't you solve this after? Okay, R raised power minus 3 is basically 1 by R. 1 by R cube. 1 by R cube is equal to 1 by 4. If you take the reciprocal, R cube is equal to, R cube will be equal to 4 after taking the reciprocal. If you take the cube root on both the sides, R will be equal to 4 raised power 1 by 3. Let's assume R is to be calculated in angstroms. So this is the answer of the question. Right? This is the answer of the question. This is the bond length between A and B. Perfect? Right? So I hope if a question is asked from the curve, you can easily solve it. Just one simple statement that at the bottom, the slope of the tangent is 0. That's all. I hope this is perfect. Now guys, basically what we are doing, we are trying to understand, we are trying to study valence bond theory now, right? Valence bond theory, what it says, it explains how covalent bond is formed. And how covalent bond is formed by when the atomic orbitals of the bonding atoms, when they overlap. What is overlap? Penetration of atomic orbitals of bonding atoms into each other. That's something which we call as overlap. And due to the overlapping, what happens? Covalent bond formation takes place, right? Covalent bond formation takes place. Perfect. Now exactly we are going to discuss this overlapping in detail. What is overlapping? Penetration of atomic orbitals into each other. That's something which you call as overlapping, right? This is something which I have to tell you in detail in some time. Before that, let me tell you the rules for overlapping. Whenever two atomic orbitals overlap, whenever two atomic orbitals of two bonding atoms overlap, it leads to the formation of covalent bond. And strength of the covalent bond, that depends on the extent of overlap. More the overlap happening between the atomic orbitals, stronger is the bond. Remember this. What is the reason? You'll get the idea in some time. Right? Greater the extent of overlap between the atomic orbitals, do remember, more will be the strength of the bond. One point which I would want you guys to remember. And after the overlapping is done, the electron density, it will arrange itself in such a way that it comes under the influence of both the nuclei. What does that mean? For example, this is the atomic orbital 1. This is one more atomic orbital, right? This is atomic orbital of one bonding atom. And this is atomic orbital of one more bonding atom. Let's say they're approaching towards each other and they're overlapping. They overlapped like this. This is how overlapping took place. For example, just to make you understand, I'll be teaching you this in detail in some time, right? Over here, can I say overlapping has happened? Penetration of atomic orbitals into each other, due to which what happened? Covalent bond formation takes place. Now, my dear students, this electron density, it arranges itself in such a way that it comes under the influence of both the nuclei. So final, as a resulting shape of the molecular orbital will be like this. A resulting shape, this is the nucleus, this is one nucleus, this is one more nucleus, and electron density has arranged in such a way that it came under the influence of both the nuclei. Right? This is the statement which I'm talking about. Yeah? This is the statement which I'm talking about. Right? Now guys, before understanding all these things in detail, this was just the overview of the things. Before understanding these things in detail, let's try to go for the types of overlap, from which you can understand exactly how this overlapping exactly happens. Right? Perfect. So my dear students, we have got two things over here. Overlap is of two types. One is called as axial overlap. One is called as parallel overlap. What is axial overlap? Axial overlap happens between the atomic orbitals along the axes. Do remember, due to axial overlap, always sigma bond formation takes place. The bond which gets formed due to axial overlapping, that's called as sigma bond. In case of parallel overlapping, what happens exactly? In case of parallel overlapping, atomic orbitals, they overlap, by keeping their axes parallel. By keeping their axes parallel. By keeping their axes parallel. And do remember, due to parallel overlapping, which type of covalent bond is formed? Either pi bond is formed or delta bond is formed. Right? Covalent bonds are basically of many types. One is called as sigma bond, one is called as pi bond, one is called as delta bond. Due to axial overlapping, always sigma bond formation takes place. Due to parallel overlapping, always pi bond takes place or delta bond can take place. Now let's understand properly in detail how these sigma and pi bonds, they are being formed. So first of all, I am marking the heading over here as axial overlapping. This is the first type of overlapping which we are going to discuss. Axial overlapping. So my dear students, in case of axial overlapping, what happens? I'll say atomic orbitals penetrate into each other along the axes. And let me tell you, due to axial overlapping, what happens? Due to axial overlapping, always, which type of covalent bond is formed? Sigma bond is formed. Sigma bond is one type of covalent bond, basically. Now, let's try to understand how this axial bond formation, how this axial overlapping happens. My dear students, the first type of axial overlapping, which I'm going to discuss with you, that's what I'm calling SS overlap. SS overlap. What does that mean? That means the s orbital of one atom and s orbital of one more bonding atom, they are going to come closer. They'll do the head-on overlapping. Axial overlapping is also called as head-on overlapping. It's also called as head-on overlapping as well. Now have a look. SS overlapping. Let's assume this is the s orbital of one atom and this is s orbital of one more atom. Okay? Perfect. S orbital of one atom, s orbital of one more atom. Let's assume this is the internuclear axis, which is generally taken as z-axis. Z-axis is generally taken as internuclear axis. Okay? Let me write it over here so that I get space. This is z-axis, which is my internuclear axis over here. Now, these atomic orbitals, what do they have to do? If I ask you whether these atomic orbitals are approaching along the axis, yes. So what kind of overlap they'll do? They'll do the head-on overlap. They'll do the head-on overlap. They'll do the axial overlap. My dear students, now this axial overlap, it can happen in two ways. It can happen in two ways. Understand? I'm going to give some signs over here. Let me write positive over here. Let me write positive over here. These are not the charges. These are not the charges. These are not the charges. What is the significance of these signs? You'll get the idea in some time. Let me tell you two things can happen over here. Either positive overlap will happen or negative overlap will happen. Always remember, a bond is formed always by the positive overlap. Through negative overlap, bond is not formed. Positive overlap, it leads to the formation of bond. It leads to the formation of bond. Which bond I'm talking about? Formation of covalent bond. Positive overlap. Negative overlap, it does not lead to the formation of bond. Okay? My dear students, now the point is, how can I show whether the overlap happening between the two is positive or not? That's why I've given the signs over here. This is positive, this is positive. If I'm keeping same sign, it represents positive overlap. It represents positive overlap. Or you call it as in-phase overlap as well. You call it as in-phase overlap as well. Now, they are going to overlap. Now they are going to overlap, right? This is positive, positive, right? Now, my dear students, what has happened exactly? If I ask you what has happened, penetration of atomic orbitals into each other, right? Axial overlap, head-on overlap. It leads to the formation of what? It leads to the formation of sigma bond, right? It leads to the formation of what? It leads to the formation of sigma bond. So over here, which bond got formed? Sigma bond got formed. And how does it look like? The electron density will arrange in such a way, that it comes under the influence of both the nuclei, right? So final representation of it will be like this. Okay, this is the electron density, which came under the influence of both the nuclei. And which bond got formed? It is basically the sigma bond which got formed by the head-on overlapping. Okay, So this was SS positive overlap. Now, if I ask you how to show SS negative overlap, how to show SS negative overlap, then you just have to change the sign. If this is positive, you have to show it as negative. You have to show it as negative. Okay, you have to show it as negative. So positive, negative. Perfect. Opposite signs. So you call it either as negative overlap or you call it as out of phase overlap. You call it as out of phase overlap. And due to negative overlap or out of phase overlap, covalent bond formation, that does not take place. Okay. So this was your SS positive overlap, SS negative overlap. Second, that is SP overlap. SP overlap. From the name itself, you can understand this. One of the S orbital of one atom and P orbital of one more atom, they are going to penetrate into each other. Let's assume this is S and this is P of one more atom. Let's say this is positive, this is positive, this is negative. So which overlap this is? First of all, is it the axial overlap? Yes, this is the axial overlap. They are going to penetrate into each other along the axis. This is the head-on overlap. And same sign on same side. So first of all, it is the head-on overlap. It is the in-phase overlap, or you call it as a positive overlap. Due to which, is this axial overlap? Yes, this axial overlap. Axial overlap leads to the formation of sigma bond, right? It leads to the formation of sigma bond. So this is the common electron density over here. This is something which you call a sigma bond over. This is sigma bond, right? If you want to show the negative overlap, out of phase overlap, this is in phase overlap, right? This is in phase overlap. Now out of phase overlap. This, for example, positive. This is negative. This is positive. Opposite sign on same side. Opposite sign on same side. Opposite sign on same side. You call it as negative overlap or you call it as out of phase overlap, which does not lead to the formation of any covalent bond. Perfect. Then, talking about the third overlap, third axial overlap, that is PP overlap. PP axial overlap. I'm just talking about axial overlap right now. Okay? I'm just talking about the axial overlap right now. Let's assume this is your PZ. Let's assume this is P orbital of one more atom. These are two bonding atoms. Basically, they're P orbitals. They are coming, they're approaching towards each other, and they're approaching along the axes, right? Let me give the signs as well. Let's say this is negative. Let's say this is positive. Let's say this is positive. Let's say this is negative. First of all, tell me whether this is axial or parallel. This is head-on overlap, axial overlap. It will lead to the formation of sigma bond. So sigma bond will get formed. Whether they will show positive overlap or negative, it's going to be positive overlap, or you can call it as in-phase overlap. This is in-phase overlap. And how exactly the molecular orbital looks like? It will look like this. Have a look. This is showing negative. This one is negative. And in the middle, this is positive, right? This is positive in the middle. So due to axial overlapping, what happens? Due to axial overlapping, what happens? Sigma bond gets formed. So it's again a sigma bond, which got formed by positive overlap between PZ and PZ. Let's say this was PZ orbital. Let's assume this was one more PZ orbital, right? If I want you guys to show the negative overlap, you can do that as well, right? You just have to change the sign. Let's call this positive. Let's call this as negative. Let's call this as negative. This as positive. Opposite sign on same side. So this is what you call as out of phase overlap, or you call it as negative overlap. Negative overlap or out of phase overlap. And negative or out of phase overlap, it does not lead to the formation of bond. I hope this is clear. I hope this is clear. Yeah? Perfect. Now, my dear students, you got to know due to axial overlapping, sigma bond formation takes place. Perfect. Now we have to understand the parallel overlapping. Now we have to understand the parallel overlapping. Parallel overlap. Through parallel overlap, which bond gets formed? Either pi or delta. Majority of the times it's going to be pi bond. Through parallel overlapping, pi bond gets formed, right? Perfect. The first example which will exactly show us how pi bond gets formed through the parallel overlap. Case number 1. Now I'm only going to show the positive overlaps. I'm not going to show the negative overlaps. That's understood now, right? Okay. So first of all, PP parallel overlap. PP parallel overlap. In this particular overlap, the XCs have to be parallel. Let's say this is p orbital of one atom. This is one more p orbital of one atom. These are the XCs which I'm talking about, right? Now, my dear students, these atomic orbitals of two bonding atoms, they are going to come closer, right? With their XCs parallel. So this kind of overlap is something which I'll be calling as parallel overlap. Now, since I have to show positive overlap, let's give them the sign. This is positive, this is negative. This is positive, this is negative. Same sign on same side. So I'll be calling it as in-phase overlap, positive overlap, right? In-phase positive. In-phase positive. Now, imagine as if when they approach each other, the lobes bend towards each other. Imagine as if the lobes have bent towards each other, like this. Imagine as if the lobes have bent towards each other. So what has happened? This is the overlap over here. This is the overlap over here. Perfect. And this particular overlap is something which I call as parallel overlap. And through parallel overlapping, which bond gets formed? It is basically the pi bond which has got formed over here. It is basically the pi bond which has got formed over here. And finally, how do I represent it? See finally. This is the electron density over here, and this is the electron density, so I'll be representing it like this. This is the electron density, and this is the electron density, right? My dear students, in the middle, if you observe things in the middle, there is basically one plane. There is basically one plane. So basically there's a plane, it is a plane, and if this is a plane, above which there is electron density, and below which there is electron density. On this plane, there is no electron density. On this plane, there is no electron density. And that plane on which there will be no electron density, you'll be calling that plane as a nodal plane. So how many nodal planes are here? There is one nodal plane. Okay. Which bond got formed over here? This is something which I call as pi bond. Now, which pi bond this is? This is something which I call as p-pi bond. This is something which I call as p-pi bond. I hope this is clear. Yeah, I hope this is clear. NP represents nodal plane. Okay, this was the first type of parallel overlap, PP overlap. Now, second is PD parallel overlap. PD parallel overlap. PD parallel positive overlap I'm showing. Okay, by the way, if you have to show the negative overlap, then this is positive, this is negative. Make this negative, this positive. Opposite sign on same side. Negative overlap, which does not lead to the formation of bond. Right? Okay. Now try to understand one more thing. Now it's going to be PD overlap. For example, this is the p orbital, positive, negative. Now d orbital of one more bonding atom. This is the d orbital of one more bonding atom. Give the signs. I have to show the positive overlap. If this is positive, this has to be positive. If this is positive, this is negative. Negative, negative. And this has to be positive. Perfect. Right? Now, this is again going to be what? This is again going to be a parallel overlap. And parallel overlap leads to the formation of what? Pi bond. And how the overlap looks like? See, this was your P. And this D would have penetrated like this. It would have penetrated like this. This is the common electron density over here. This is the shared electron density over here. Perfect. So this particular bond over here I'll be calling as p-pi d-pi bond. Right? Were they in phase or out of phase? This was in phase overlap. This was positive overlap. This was positive overlap. And this was parallel overlap as well. And due to parallel overlapping, which bond is formed? It is basically the pi bond which gets formed over here. Right? It is the pi bond which gets formed over here. So this is p-pi d-pi bond. Now, talking about the third overlap. The third overlap is going to be d-pi d-pi overlap. Or I'll be calling this as two-lobe interaction. I'll be calling it as two-lobe interaction. Okay? My dear students, let's assume this is the d orbital of one atom. And over here I've got one more d orbital of one more bonding atom. So I've got two bonding atoms whose d orbitals I've taken into consideration. Okay, whose d orbitals I've taken into consideration. Let me call this as positive. So this has to be negative. Let me call this as negative. So this has to be positive, right? If this is positive, this should be positive as well. This should be negative. If this is negative, this has to be negative. This has to be positive. Just to show the positive overlap, right? Now, my dear students, these lobes are going to interact. Parallel overlapping this again. And parallel overlapping, is it positive parallel? Yes, this is positive overlap. This is again in phase overlap. This is again in phase overlap. And due to this in phase overlap, due to this parallel overlap, first of all, what happens? Pi bond formation takes place, right? Pi bond formation takes place. So it's going to be like this. Right? You can give the signs as well. This is the common electron cloud over here. So since it was the parallel overlap, so pi bond got formed. Since two lobes have interacted, that's why you call it as two-lobe interaction. At the same time, this pi bond which got formed by the parallel overlap, this is something which I call as d pi overlap. So d pi bonding. One is p pi bond, one is d pi bond. One was p pi d pi. Now after this, one last, that is something which I call as, which is again d pi only. It's again d pi only. Basically, I should write dd overlap. I'm writing d pi, right? So this is not going to be two-lobe now. It's going to be four-lobe interaction. It's going to be four-lobe interaction. How it looks like. So one of the d orbitals of one bonding atom, positive, negative, negative, positive. One more d orbital of one more bonding atom. So I've got two bonding atoms who are supposed to form a bond, basically, right? Or supposed to form a bond. Perfect. Now these two orbitals, they overlapped like this. Perfect. Now these two orbitals, they are not going to overlap like this. They'll overlap one over the other. If they overlap one over the other, that means this particular lobe is going to overlap with this one. This particular lobe is going to overlap with this one, right? Similarly, this lobe is going to interact with this one, and this lobe is going to interact with this one, right? This particular interaction is called as four-lobe interaction, due to which bond is formed? It is going to be delta bond which gets formed due to four-lobe interaction over here. I hope this is clear to everyone. So quickly in the chats if it's clear. Quickly in the chats if all the things are clear till here. Quickly, people. Wait, Prajwal, I'll show you the oxygen molecules as well. Just wait. Don't jump. I'll show you the formation of oxygen, nitrogen, everything. Just wait. Do not be smart. Your teacher is smarter. Okay, let's move on. I hope all these things are clear. All right, guys, just a second. All right, few more basic things which you need to know. We are going to compare now the strength of pi and sigma bond. Let's try to understand the strength of pi and sigma bond. My dear students, do remember sigma bonds are stronger than that of pi bonds. What is the reason why sigma bonds are stronger than pi bonds? There are many reasons. First reason is, that's very simple. That is about the extent of overlap. Extent of actual overlap, that is greater than that of extent of parallel overlap. Actual overlap leads to the formation of sigma, parallel overlap leads to the formation of pi. If extent of actual overlap is more, right? You know, strength of bond, that is directly proportional to extent of overlap. More the extent of overlap, stronger is going to be the bond. If the extent of overlap in actual is more, that means the bond which gets formed here That will be stronger. That will be stronger, right? That will be stronger. This is one factor by means of which you can explain why sigma bonds are stronger than pi bonds. The reason is extent of overlap in axial is more than that of extent of overlap in parallel overlap. Yeah. Number two, there is one more reason. That is energy factor. This is overlap factor. Second reason is energy factor. Energy factor also tells us why exactly your sigma bonds are stronger than that of pi bonds. How exactly? For example, let's say this is the sigma bond over here. Right? This is the sigma bond, which is found by the direct head-on overlap. Okay? Now, over here, for example, let's say this was PP overlap, so let's make it like this. Let's make it like this. This was PP overlap, for example. PZ overlap, something like that. This was the axial overlap through which sigma bond got formed. Now, what about the pi one? Pi overlap looks like this. Sideways overlap looks like this. Your pi bond looks like this. Perfect. In between, there's a nodal plane. This is the nucleus. This is the nucleus. Right? Now, my dear students, if this is the nucleus, for example, if this is the nucleus, between these nucleus, this is the nucleus of one atomic orbital. This is the nucleus of one atom. This is the nucleus of one more atom. Now, these atomic orbitals came, right? They merged into each other, right? They formed a molecular orbital. This is, for example, a molecular orbital. This is the nucleus. This is one nucleus. This is one nucleus. This is one nucleus. This is one more nucleus of this molecular orbital. Now, as you can see, between these two nucleuses, what do we have? We have got electron density. We have got electron density. So I would say these two nucleuses, they are not in direct contact. There is electron density in between. But look at these two nucleuses. Is there any electron density in between? No, it's a nodal plane on which electron density is 0. Right? There is no electron density in between. Now imagine where will be the repulsions between the nucleus more. Over here, this electron cloud, it is becoming a shield. It is becoming a shield towards the repulsions between these two nuclei. Right? Over here, there is no shield towards the repulsions. So repulsions between the nuclei will be more here. More the repulsions, more the energy, less the stability. Less the stability means lesser is the strength of the bond. Right? So do remember, strength of sigma bond is greater than that of strength of pi bond due to energy factor as well. Perfect. Over here, there is no electron density in between. There is electron density. Perfect. There is electron density. So repulsions will be more in the second case. Repulsions more, stability less. Right? Energy more. Perfect. Energy more, stability less means energy more, stability less. Stability less means strength of this bond is less than that of strength of this particular. I hope this is clear to everyone. Now guys, if this is clear, do remember these basic points. These basic points are used to solve some questions. Look at this particular statement. For the same energy shell, axial overlap. For the same energy shell. For example, you have got 2s, they are doing the axial overlap, right? Then you have got 2s, 2p, axial overlap. 2p, 2p, they are, for example, doing the axial overlap, right? For the same energy shell. Energy shell everywhere is same. Energy shell everywhere is same. Whenever energy shell is same, extent of overlap between 2p, 2p, between p and p in general is more than that of sp overlap, is more than that of ss overlap. But which overlap I'm talking about? I'm talking about axial overlap. I'm talking about axial overlap, right? I'm talking about axial overlap. So for the same energy shell, axial overlap between PP is more than that of SP, which is more than that of SS. And you know, more the extent of overlap, more is the strength of the bond. Perfect. So you get a question based on the bond strength. One of the bond is formed by 2p, 2p overlap. One more bond is formed by 2s, 2p axial overlap. One more bond is formed by 2s, 2s axial overlap. Which bond is stronger? It is the bond which is formed by 2p, 2p axial overlap that will be stronger. Right? That is the reason why I'm giving you this. Okay? And one more statement. If the orbitals are of different shells, then the lower energy orbitals, they produce more effective overlap. If the orbitals are of different shells, for example, S and S, this is 1, this is 2. So these orbitals, I mean 1s, 2s, 1s. Right? Similarly over here, 2p, 3p, 2p, 2p. Where is the extent of overlap more? It is simple. Lower energy orbitals, they produce more effective overlap. Where do you see the lower energy orbitals? Lower energy orbitals are here. 1s. Over here there is 2s. 1s. Lower energy orbitals. Okay? Right here, lower energy orbitals, 2p, 2p. Lower energy orbitals, they produce more effective overlap. Right? Do remember this thing as well. This will be used afterwards. Similarly, when you compare the strength of pi bonds, this is, by the way, this is something which I was talking about strength of sigma bonds. Perfect? I was talking about the axial overlap. I did not talk about the parallel overlap yet. I was talking about the axial overlap. Yeah? So, strength of pi bonds. Strength of pi bond is inversely proportional to internuclear distance. More the internuclear distance, lesser is going to be the strength of the pi bond. Similarly, this is one more order which I would want you guys to remember. 2p pi, 2p pi, strength is maximum, followed by 2p pi, 3d pi. Then you have got 2p pi, 3p pi. Then you have got 3p pi, 3p pi. This is one more order from which questions will be directly asked. I'll be giving you questions in some time. This is one more order which you have to remember. This is one more order which you have to remember. Right? This is one more order which you have to remember. This is important. And one more simple thing. For example, there is a triple bond between A and B. There is a triple bond between A and B. Do remember, the one bond will be sigma and the other two bonds, they'll be pi. They'll be pi. 1 sigma and 2 pi. Let's say there are 4 bonds between 2 atoms. Let's assume there are 4 bonds between 2 atoms. Let me tell you, one of the bond will be sigma, so it's 1 sigma. There'll be 2 pi also. There'll be 2 pi also. And one more will be delta. There is 1 delta as well. So 1 sigma, 2 pi, and 1 delta. Right? Do remember always, sigma bond formation takes place first. Sigma bond formation takes place first. Sigma bond formation takes place first. And after that, pi bond is formed. Followed by pi bond. Followed by pi bond. Do remember, between 2 atoms, sigma bond is formed first. After that, pi bond is formed. Okay? At the same time, guys, there is one molecule, that is C2 molecule. This is something which I'll be teaching you in molecular orbital theory. In C2 molecule, let me tell you, both these bonds, these are pi bonds only. It is not 1 sigma and 1 pi. Both these bonds are pi bonds only. There are 2 pi bonds in C2. There are only 2 bonds and both the bonds are pi. Why is it? The answer you'll be getting in molecular orbital theory. Right? The answer you'll be getting in molecular orbital theory. Perfect? Now, guys, there is one more statement which I would want to share with you. Right? Carbon, double bond carbon, you have seen many a times. Right? Silicon, double bond silicon, it is rarely found. What is the reason? What is the reason? Because this pi bond over here, it is basically 2p pi, 2p pi, pi bond. Right? It is found by 2p pi. It is found by 2p and 2p. By parallel overlapping of 2p and 2p. Whereas this particular pi bond, it has to be formed by 3p and 3p parallelly. And you know, extent of overlap, or few minutes back I told you, strength of 2p pi, 2p pi is greater than that of strength of 3p pi, 3p pi. Right? Due to which strength of 2p pi, 2p pi is greater than that of strength of 3p pi, 3p pi. That's why this particular bond is stable. Right? So this particular carbon double bond carbon is frequently seen, whereas this is rarely observed. Right? Whereas this is rarely observed. My dear students, all these things, all these overlaps which I told you, let me try to show all these overlaps in the form of molecules now. Now this is going to be something important which you have to remember. Yeah? Have a look, people. For example, I'm taking one molecule as F2. I've got F2 molecule. Let me exactly show you how the formation of F2 takes place. How this F2 molecule is formed. Yeah? How this F2 molecule takes place. Have a look properly. Understand. My dear students, you have got 2 fluorine atoms first of all. Let's say this is one fluorine atom and this is one more fluorine atom. These are 2 fluorine atoms which I took. If I ask you what is the outermost configuration of fluorine, it is going to be 2p5. Outermost configuration of fluorine It's going to be 2p5. Okay, it's going to be 2p5. Now, dear students, let me show you how this 2p5 exactly looks like. Let me show you how this 2p5 exactly looks like. So there'll be basically 3 orbitals here. Similarly, there'll be 3 orbitals here, right? This is 1, 2, 3, 4, and 5. Similarly, this is 1, this is 2, this is 3, this is 4, this is 5. Now, I have to show you how these 2 F atoms will combine. They'll lead to the formation of F2 molecule. They'll form a molecule. Okay, perfect. Now have a look. Let me first of all call this as 2px. Let me call this as py. Let me call this as pz. Similarly, let me call this as px, or just wait. Just wait. Let me call this as pz. Let me call this as px. Let me call this as py. Similarly, let me call this as pz. Let me call this as px. Let me call this as py. So what exactly is going to be happening? Have a look. If you look at this particular configuration, there are 3 p orbitals. One is pz, right? Let's assume this is your z-axis. So it is going to be your pz carrying 1 electron. Pz is carrying 1 electron. Perfect. Pz is carrying 1 electron. Now similarly, px is carrying 2 electrons. This is for example your px. It's carrying 2 electrons. Similarly, you have got py as well. You have got py as well, which is again carrying 2 electrons. Perfect. Again carrying 2 electrons. 1 electron, 2 electrons, and 2 electrons. Similarly, my dear students, look at this fluorine. Look at this particular configuration. Look at this particular configuration. Pz carrying 1. Pz carrying 1. Pz carrying 1. So I would say this Pz of another fluorine will come from this side and will do the overlap. Which overlap it is? It is head-on overlap. So sigma bond has got formed. Sigma bond has got formed. Now, my dear students, look at other things as well. Px is carrying 2. So this is Px, which is carrying 2 electrons. And similarly, there is Pz as well, sorry, Py as well, which is carrying 2 electrons. Let's assume that this is your Py over here, right? So look at this particular overlap. Is this head-on overlap or this is parallel overlap? This is head-on overlap, this axial overlap, which leads to the formation of what? It leads to the formation of sigma bond. So this is how your F2 molecule exactly looks like. This is how F2 molecule exactly looks like. Perfect. So how do I represent it? This is F, this is one more F. Perfect. This is F, there is a single bond and there is one more F. I hope all these things are clear to you. This is how your F2 molecule is formed. Yeah? Is it clear, people? Quickly once, let me know in the chats. Who is this nonsense Murtaza Nazir? Bro, why are you spamming? These type of people never qualify the examination, I'm telling you. Okay? I mean, from some other channel they are studying, they're coming here to spam. What is the logic? Nonsense. You tell me the logic why you're coming here. Are you the paid user? Is someone paying you to, spam all this? Nonsense. You should have been in front of me. Okay, so this is how F2 molecule formation takes place, and this is how your valence bond theory. This is how your valence bond theory, it explains the formation of F2 molecule. Yeah? Perfect. Similarly, let me show you how exactly O2 molecule formation takes place. Let's see how O2 molecule formation takes place as per VBT. Now you should be able to know exactly how O2 molecule formation takes place. Understand properly what I'm going to say. My dear students, understand. In order to form an O2 molecule, let's say this is one oxygen atom, this is one more oxygen atom. Now these two oxygen atoms, they'll approach each other, right? Their atomic orbitals will overlap. They lead to the formation of bonds. You know that. Now, first thing, if I ask you, what is the outermost configuration of this oxygen? This is 2p4. What is the outermost configuration of this oxygen? This is again 2p4. Correct? You must be knowing this. Now, how do I mention this 2p4 configuration? And how do I mention this 2p4 configuration? Understand properly what I'm going to say. This is important. Okay? So, these are first of all 3 p orbitals. Again, these are 3 p orbitals. 2p4 configuration. This is 1, this is 2, this is 3, this is 4. Similarly, this is 1, this is 2, this is 3, and this is 4. Correct? As simple as that. Now, my dear students, let me call this as pz, let me call this as px, let me call this as py. In the similar way, let me call this as pz, let me call this as px, let me call this as py. Perfect. Now, how they exactly look like? If I talk about this particular oxygen, if I talk about these 3 orbitals, one is your pz. Let me assume this is your pz, carrying 1 electron, right? Px, let me assume this is px, carrying 1 electron, right? And this is py. Let me assume this is py, carrying how many electrons? Carrying 2 electrons, correct? Let me give you different shades of these orbitals so that you can understand this, so that there won't be any sort of doubt at all. Okay, so one is your pz, px, and py. In the similar way, one more oxygen atom. If I talk about its pz would have come from this side and done the axial overlap, right? So over here, which bond got formed? It is sigma. So sigma bond got formed. After that, my dear students, have a look. Have a look. Px is carrying 1 electron. So this is, for example, px carrying 1 electron. And similarly, there is py as well, which carries 2 electrons. This is py, which carries 2 electrons. Now, if I ask you one simple thing over here, py is carrying 1 electron, sorry, px is carrying 1 electron, even this px is carrying 1 electron. Their axes are parallel. So can I say they'll show the parallel overlap here, and parallel overlap leads to the formation of what? It leads to the formation of pi bond. So how exactly you are going to represent it? This is one oxygen atom, this one more oxygen atom. Oxygen. Sigma bond got formed first, and after that, a pi bond got formed. So this is how your O2 molecule exactly looks like, as per valence bond theory. Right? Right, people? One last example I'll take. Okay, last example is N2 molecule. N2 molecule. So this is something which you should know now. If I talk about the configuration of nitrogen, it is 2p3 configuration. One more nitrogen, it has got 2p3 configuration. Perfect. So just make the diagram over here. 2p3, correct? 1, 2, and 3. Similarly, this is 1, 2, and 3. Let me call this as px. Let me call this as py, and let me call this as pz. In the similar way, this is px, this is for example py, this is pz. Now, my dear students, have a look. Look at these 3 p orbitals. This is for example your pz carrying 1 electron, right? This is for example your px carrying 1 electron. This is for example your pz carrying 1 more electron. Perfect. Now, similarly, look at this particular nitrogen which has got these 3 p orbitals. Again, pz, py, px. This is pz, right? Overlap leads to the formation of sigma. Perfect. Then you have got px. This is your px. This is a px carrying 1 electron. And then you have got pz, which is also carrying 1 electron. Pz is also carrying 1 electron. So overlap between the two. This is parallel overlap. In the similar way, I must say, just a second. This is the overlap. This is the parallel overlap between these two. And apart from that, there will be parallel overlap between these two as well, because their axes, they are parallel. These are parallel, so parallel overlap. These are parallel, so parallel overlap. So how do you represent it? This is one nitrogen atom. There you have got one more nitrogen atom. These are 2 nitrogen atoms. First, sigma bond got formed, and after that, 2 pi bonds got formed. This is one more. So this is your N2 formation as per your valence bond theory. I hope this is clear to everyone. Yeah? Perfect. Is it clear, people? Is it clear, people? Perfect, guys. So with this, your valence bond theory is over. I think this much is enough for today. In the next session, there are three topics left now. One is hybridization, one is valence shell electron pair repulsion theory, and one is molecular orbital theory, right? And some bond parameters as well. That's something which we shall be discussing on Saturday. On Saturday, coming Saturday, day after tomorrow, Saturday 5 p.m. I'll take one more session, which is going to be chemical bonding part 2, in which we'll be finishing this particular chapter. And we'll do all the PYQs which have been asked from this particular chapter as well. I hope whatever I've taught in this particular session, everything is clear, right? That's great, Zad. Well, Zad was my last year's YouTube student. He used to follow me, I remember. Glad that you are in NIT Nagpur. Glad about that. All right, guys. So I'll see you day after tomorrow then. So day after tomorrow, we'll complete this chapter. We have got 3-4 topics left. So let's try to complete them. Okay? Hello, guys. Take care. God bless you all. See you in the next session. Bye-bye. See you on Saturday. Do join that session. That's again important.